Good morning.
Evet evet yazıyor hocam. Web sayfasındaki
Ses. Okay. I would like to thank the organizing committee for this nice conference. And we would like to start today's section. We have 3 speakers today, and it's going to be online. First speaker, Catherine Frank. Its area condensed matter physics, yielding an investigation magnetic atomate change on superconductors atom by atom.
Yeah, thank you very much for the kind introduction, and first of all, also for the invitation to speak here. I'm not sure that I can share my screen if the other screen is still there, but let me try. No, I cannot. I think someone needs to. Let me try. Do you see my screen now? Okay, I assume that you see, and I assume that you're seeing the right screen. So yeah, thanks again. As has been kindly pointed out already, I'm going to talk about these magnetic atom chains, and you see already where we are heading for. So this is a chain that has been really deliberately set up atom by atom with the tip of a scanning tunneling microscope. And what you see here are individual iron atoms placed on a superconductor, which is the niobium diselenide. I would first of all like to thank the people who did the work really, and this is Eva Liebhaber in her PhD thesis work, and it's really step by step not only building these atomic chains, but it's also kind of a way toward her PhD degree. And she was joined by Lisa Rütten, who's now taking over the project, and Gail Richt as a postdoc. And everything has been discussed and in a very fruitful and enjoyable collaboration with the theory group of Felix von Oppen, and in this case, his PhD student, Jakob Steiner. And the samples, it's really important to have super clean niobium diselenide samples. They come from the group of Kai Rosnagel in Kiel. So why are we interested in these single atoms and even building these magnetic atom chains? And let me start in a simple picture, because I know this audience is very diverse and you come from very different fields. But maybe, you know, at least superconductivity is not only this phenomenon when you cool down a material that the resistance drops to 0 below a certain temperature, but also that a superconductor would be, or that a magnet would be levitating on top of a superconductor. And the reason for this is that it is expelling the magnetic field lines perfectly, so it's really a perfect diamagnet. And this is, of course, on the macroscopic scale, but what you could imagine is that making this magnet tiny, tiny, and tinier, and the smallest magnet that you may imagine is, of course, a single atom. And this is what we are fundamentally interested in what really happens at the single atom scale. So you could say that, first of all, we would like to understand this fundamental physics of placing an individual atom on top of a superconductor. And obviously, there will also be some interaction. We don't describe it in terms of magnetic field lines anymore, but in terms of exchange coupling. And this is something that I would like to explain the next few slides. And then at some point, more recently, it has been suggested that actually these chains of magnetic atoms, they become very interesting. Not only that these are kind of quantum spin chains on top of a superconductor, so that you can again study fundamental physics, but also it has been discussed in terms of topological superconductivity, and this is a topic that recently has gained a lot of importance. So why these atomic chains and topological superconductivity? So basically, motivation of this comes from quantum computation. And of course, in a quantum computer, you want to have this superposition of quantum states. And in this, you kind of want to store your information. Now, the problem is of many of these quantum states is that they decohere on extremely short time scales. Now, the idea is that basically, if you can somehow separate this information, so kind of store this information non-locally, that is how you can kind of topologically protect your qubit. And this is kind of the idea of these chains. If you have a perturbation on one side, it just doesn't perturb the other one, and therefore your quantum state is indeed stable. Now, how to realize this are then these one-dimensional, or one possibility is these one-dimensional at-atom chains on top of a superconductor. And at the end of these chains, there's this so-called Majorana states that are going to be built up. Now, how can we actually understand this Majorana states in this more simple picture? So let's think about this chain, how we are going to separate this information. And that is the so-called Kitaev chain. And in a simple model is, imagine that you have here your atoms that are placed in a, now it's just a freestanding chain. And here you would have your fermionic operators. But mathematically, what you do is you do a trick and you place here two operators. And these are the so-called Majorana operators. And they basically means that here you have to do that Z dagger equals C. Now, these operators, because they are non-fermionic, they are kind of protected. And how do you create such a chain? Well, how do you do this? In principle, as I said, these are atoms. And now you need to kind of protect these quantum states from the environment. And therefore, you use a superconductivity induced in the chain. And this then can protect your Majorana states at the very ends of the chain. All right, let me also point out that it's a solid state representation of these Majorana zero modes. And since this conference is very diverse, also in terms of people being interested in high energy physics, I mean, there was also this interest in looking for Majorana fermions. And the idea was that there you also look for the properties of the particle being equal to the whole. And now in the solid state analogon, of course, we are doing something similar in a kind of quasi-particle picture, what we are looking for. So again, creation and annihilation operator kind of have to be the same. And that means that if we are looking for an experimental realization, how to measure this, this should be an excitation at zero energy. Otherwise, this concept, of course, doesn't work. So we are looking for zero energy excitations in atomic chains on top of a superconductor. And this is basically the experimental realization that has been put forward. And well, how do you then do this? I mean, you need to somehow build a ferromagnetic chain on top of a superconductor. However, it was really ferromagnetic. And in a very simple picture, you have the Cooper pairs of the substrate. They would scatter on it, but nothing would happen because they can't scatter on that. But if you induce spin orbit coupling, then let me just picture it like in this very simple PowerPoint view, your spins are partially free to rotate, and then you can scatter into this chain and induce topological superconductivity within the chain. And this actually has been realized, and this is the seminal paper by the Ali Yazdani group a couple of years back. So what they did is they grew iron chains on top of a lead superconductor. Here you can see STM images. This is the lead substrate, and you can see terraces with single atom step height. And then they deposited iron on top, and this iron forms by a self-assembly process atomic chains. And well, now you have to, of course, check for the properties. And what they did is, and this is what I would like to use as an experimental technique also in the remainder of the talk, is scanning tunneling spectroscopy on these chains. So what it means is after taking your STM image, you can place the tip somewhere and take a spectrum, which means that you record the differential conductance as a function of bias voltage, and that's often equal to the energy. So you see when you measure on the superconductor, the superconducting energy gap. So the width is of course corresponding to the pairing energy in the superconductor. And then when they measured on the chain, they found that really at zero energy, there's a little peak. And this is what I just tried to explain before. We are really searching for zero energy excitations. Additionally, if you remember, what I said is that you want to have these states separated at the very chain ends. So basically, it means you should look for the zero energy excitation only at the chain ends. And here what they plot is the differential conductance signal at zero energy along a chain. So this would be a zoom on one of these chains. And it's really just localized at the very chain ends, while other energies, they have a continuous distribution along the chain. So this has been a suggestion of a Majorana state at the chain end. The other side of the chain is not shown here, but it's also there. And so this has been really discussed in a lot of theoretical papers, but also there have been follow-up experimental papers to confirm this interpretation that you have the formation of zero energy states in these iron chains. And there are a lot of indications that really point to this interpretation of Majorana states and a topological gap that has been induced in the chain. Now, as you can see here, these are really densely packed chains of iron atoms. So basically what it means is that these d orbitals of the iron chains, they couple by direct exchange, and you have really a ferromagnetic chain. Now, but there's a possibility of a different approach. And this is starting from atoms that are more separated from each other. And this is what we call a dilute magnetic atom chain. And there, what I would like to introduce in the next few slides is that these induce also some exchange coupling with the superconducting substrate, these so-called U-Shiba-Rusinov or YSR states. And they eventually form bands inside the superconducting energy gap. So here it's a function of energy. We have the superconducting energy gap. This would be, let's say, a single U-Shiba-Rusinov state inside the gap, but then it forms bands if you go to a chain. And eventually they may overlap with the Fermi energy. And then there's also a theoretical prediction that had been put forward in these two publications that you can also induce topological superconductivity and Majorana zero modes. So, but in order to induce these bands, what we have to do is we have to first understand the single atom. And what I just said before is what is called the U-Shiba-Rusinov state is what I would like to explain now in this slide. So essentially what you could think of is the smallest, the tiniest magnet that you may imagine, namely a single magnetic atom on top of a superconductor, as for example sketched here. Now, what it does is, so here you can see the quasi-particle density of states of a superconductor. And as I said, it has a gap around the Fermi energy, which with the size that is scaling by the pairing energy delta. If you now have a single magnetic impurity on top, what you could say is that, well, basically you have a spin there, and this spin is now acting on the Cooper pairs, which have, of course, a spin up and a spin down electron in their component. If you, for example, assume a ferromagnetic exchange coupling, this means that kind of in a very simple picture, you kind of pull on one of the electrons and repel the other one. And therefore, eventually, you get a bound state inside of the superconducting energy gap. Or in other words, then it is easier because you have a local perturbation, a local weakening of the superconducting condensate. Therefore, you can tunnel already at lower energies into the superconductor. And now this is always seen as a pair of states symmetric in bias around the Fermi level because you still have some particle-hole symmetry inside of your system. But eventually it could have slightly different heights due to potential scattering that comes in on top of this exchange scattering. Now there's a equation that has been derived then independently back in the 1960s by Yu, Shiba, and Rusinov, and that's why these states are called after these three guys. And they basically say, well, of course, the energy where you find these states is depending on the exchange coupling strength, this Shiba, the spin of the magnetic atom, and this is the normal density of states. So this is the exchange coupling parameter. And then, as I mentioned briefly, there's also potential scattering, but this is often neglected when you just want to look at the experiments in a more conceptual way. Okay, let me just sketch it in slightly more detail as well. So you have this single magnetic atom, here you have the Cooper pairs, and if you have a very weak interaction strength, then basically you just do a small perturbation to the system. Now, if you increase your coupling strength, then eventually you could say that you have strong coupling, and what it means is that you can locally break Cooper pairs, and in other words, you bind the quasi-particle to the impurity site. And well, apparently there must be some transition between weak coupling and strong coupling. And at this, there's a critical point that we also call a quantum phase transition, where we go from this weak coupling regime to the strong coupling, or what we also say that this is an unscreened spin and this is a screened spin because you have bound your quasi-particle to the side. And if I refer to the previous slide where we have looked at the energy of this U-Shiba-Rusinov state inside of the superconducting energy gap. So here you can find the gap. This axis is the energy, and here we plot it as a function of the exchange coupling strength. So basically, as I said here before, there must be some critical coupling strength, and at this particular transition, these states are the same in energy. Below that, you prefer the unscreened state, and above, you prefer the screened state. And you can also see here that this is a zero energy excitation. However, you should never mix it up with the Majorana state. All right, so here we are in the weak coupling and here we are in the strong coupling regime. Okay, so now let's see. So this is the fundamentals of these Yushida-Rusanov states. And as I said, that basically where we are heading for is understanding not only the single atoms, but going from there to more complicated structures, namely going, first of all, I want to explain how two atoms, these states can hybridize. And then I want to go atom by atom from 1 to 2 and then to longer chain ends. And I guess that's maybe the long chains I may not be able to cover anymore. All right, so let's go to our real systems. So what we've done is we have put manganese atoms on top of your superconducting lead-001 crystal. So in an STM topography, you can find the atom here as a slight protrusion. Now this actually looks boring, it's just a blob. But then when we look into our spectroscopy signal, which means the differential conductance as a function of bias voltage, then we find here in the background on the plane surface, there's a superconducting energy gap as we expected. And I should point out that this gray region here is because we also use a superconducting tip. So we, of course, if we want to tunnel, we have to break both a Cooper pair in the tip as well as in the substrate. So I will just pretend that we can just cut out this region in the following. Now then, this is the region where the superconducting tip of the substrate is. And there's then, when we measure on top of the atom, a very pronounced state. And as I said, it needs to be symmetric in bias voltage. And there it is. So this is a very pronounced state. But then if you look closely, actually, you could say that, well, very close to the superconducting energy gap, there's a shoulder. And if we go lower in energy, there's also another state. And again, you find it symmetric in energy. So therefore, we've labeled these states just alpha, beta, and gamma. And now I would like to convince you that these are really states there and not just that we are looking at a strange shoulder here that's not meaningful at all. So what you can do in an STM is now set your bias voltage precisely to these energies where you find the peaks and then record immediately the differential conductance signal. And by that kind of map out the structure of these states. So as I said, topography looks boring. And here are now measured at the energy, the differential conductance signal. And actually you can find nice shapes. So this clover-like shape, even for the alpha state that we found here at the very, close to the BCS gap. Then the very strong state that is also strong in the differential conductance. And also this faint state here has a particular shape. And now looking at it, the first time I was thinking like, well, this looks like d orbitals like you painted in your physics textbooks. But of course, they are larger than the d orbitals itself, and this is very weird. However, let's consider the following simple model. I mean, you place a manganese atom on top of some crystal, and actually locally, the crystal field breaks the symmetry. So if I sketch it in a simple way, this is the manganese atom and the pseudo three-dimensional view. You have the quadratic lattice around and the one atom also underneath. So in manganese, you have 5 electrons in the D shell. And of course, in vacuum, these are all degenerate, these states. But when we put it into this environment, the crystal field breaks the degeneracy. And then we still have to distribute our 5 electrons among these orbitals. Now, the dx square minus y square orbital, you can imagine, is facing these neighboring atoms as closest distance. And this is why this orbital is pushed up the most in energy. Then comes the dz square orbital, because there's an atom below. And then almost degenerate remain these orbitals, which are sitting kind of on the diagonals in between. All right, and each of these single levels still keeps a single occupation of an electron. And now this is exactly the exchange scattering potential that can interact with the superconducting substrate and give rise to these Yushida-Rusanov states. And if we then measure it, you can find the same symmetry looking kind of from the top with the STM tip, and it inherits by this scattering the same symmetry of the individual orbitals. So this is the dx square minus y square. The dz square is also pointing up the most toward the STM tip. And again, if I do a superposition of these states, you can find again a clover shape with these orbitals which have the Z components. So this already explains on why we have these shapes. So basically electrons from the substrate scatter off from the magnetic impurity, and therefore you inherit the very same symmetries. But as I said, it's not the d orbitals itself, it's the symmetry of the scattering potential, because the extent of the states is much larger than an individual d orbital. It's on the length of 1.6 nanometers. But this gives us the opportunity to think about coupling of these states if you put two atoms very close to each other. And this is what we are going to look at now. So we have placed two manganese atoms rather in close vicinity. And then what you see is that as comparison, I show the spectrum that had been taken on an individual, so separated atom. But then we measure on one of these atoms that's located in one of these dimers. Then you can find overall, at first sight, the peak shape is very similar. But at close inspection, you can find that here's a shoulder and there's also a shoulder. So everything kind of seems to be split, also this low energy state. And again, to show that the splitting is a real effect, and also to see symmetries of the scattering potential, what we do is now we also plot the differential conductance again. So for comparison, again, up here, I show the single atom and then the dimers. And well, actually, you see that this tiny energy splitting still shows you very different maps in the differential conductance signal for each and every of these orbitals. And as a first sight, you can say that here you have enhanced intensity along the connecting line, while here you have a nodal plane. And let me just illustrate it as the example of this very last state that's lowest in energy. We said previously that it is actually a combination of these orbitals, and the ones that give rise to this clover shape is the dxz and the yz orbital that we can kind of measure with the STM from the top. Now, if you put two of these together, let's say then just from the top view, this PowerPoint sketch tells you like you have a clover shape of the individual atom. You put two of them close to each other, and in a very simple model, you do a linear combination of these orbitals. And once, of course, you do the symmetric linear combination, which means that you have enhanced intensity across the connecting line. And once you do the anti-symmetric combination, where you have the nodal plane. And just looking at these very simple sketches, I would say that it has a very good agreement already in experiment. So what it means is that even with these kind of complicated Yushchi-Baruzanov states, you can adapt very simple models that you have, for example, learned in your atomic and molecular physics classes, where in order to construct a hydrogen molecule, you also just take the linear combinations of the individual atomic orbitals. And this is what you can also do for these Yushchi-Baruzanov states. So in principle, this is how hybridization can work. And let me now go and see if we can actually use this understanding for longer chains. And here we've changed our substrate. We cannot measure on lead for technical reasons these chains. At least not atom by atom. So that's why we have used this niobium diselenide. It's a van der Waals material. It has this stacked structure, but still it has a critical temperature of 7 Kelvin, similar to lead. And actually, I maybe forgot to mention, we are measuring at 1 Kelvin. So we are sufficiently below this critical temperature. So it is a superconductor. We can measure the superconducting energy gap. It looks slightly more complicated because it's an anisotropic superconductor, but we don't need to care about this peak structure. For the moment, again, we measure with a superconducting tip.
You have 5 minutes.
Okay, thank you. In addition to the superconducting properties, it has a charge density wave that I don't want to go into detail, but this is just an additional modulation of the atomic STM images in top of the atomic corrugation. You also see that there's an almost commensurate, so it's an incommensurate charge density wave. Okay, and the advantage of this is now really that we can place individual iron atoms, and then they, of course, land statistically on top of the surface. And with the STM, we can then take these atoms and shuffle them in the way we want and create these very nice chains. What I said before is that we have the charge density wave, and now what we are going to do is we will always place atoms with the same registry with respect to the charge density wave, so on top. So for example, one atom would be here and the next one would be here, and one could be also here. And you already see that the distance between the atoms is quite large. It's on the order of 1 nanometer. So there's really no direct exchange. So this is what we call the dilute limit. Okay, let me first go to a single atom that we have to characterize. It's very similar to, in the sense of the physics of what is happening on lead, a single atom. Here you see the STM image inside. And then again, we take spectra. And for comparison, the gray spectrum is again on the background. But then when we measure on the atom, you can find that there are states inside of the superconducting energy gap. And maybe this is actually better seen if we take like a spectra along a line, so along this line. And then you can see that outside you see only the superconducting energy gap when we are far away, but when you come close to the atom, you see these U-Shiba-Rusinov states very well in this line plot. Now, if you put two atoms next to each other, so for example, in this distance, as I mentioned before, the spectrum changes significantly. And actually, you have many more peaks. And if you look in a zoom, so here you find that you basically see a doubling of the number of peaks. And we can just zoom into this region. You can find that an original state that was on the individual atom now again splits into two. So, and we have again more than one state, so that we can label again with alpha and beta, for instance, and you see a splitting. So let me just say that in this case, we can apply this model again. So although we cannot so nicely identify the orbitals, we can again say that we have these linear combinations in the symmetric and antisymmetric case. And indeed, we can also not only see it here in the line profiles, but also in mapping out the differential conductance signal again, for instance. Here we find a nodal plane, but here we do not. And this is very similar to the case that I wanted to explain on the manganese atoms on lead. So we can identify these orbitals. We can also do it for the different states. And basically, this tells us that hybridization works. Okay, so let's go to, I will jump over this. Let's go to longer chains then. So in principle, what we can now do is we can start with a single atom and then add atom by atom on this chain length. And here you can see just a series of these spectra. And what you can find is that these line spectra that are plotted here, they really change dramatically upon addition of one of the atoms. And it really changes along the whole chain. And you can really see you're always adding more states to the chain. Eventually, you cannot distinguish them separately anymore, so you cannot identify these hybrid states. But what still is preserved always is that you change everything along the chain and you preserve some horizontal mirror symmetry. So even adding one atom here changes the whole spectral properties along the chain, preserving the symmetry. Additionally, we can add it up and you really find a delocalization along the whole chain. And this is kind of telling us that we have band formation, and we can also map it out. So for example, here we have this, I think it was the 9-atom chain. You can find the DIDV signal homogeneously basically along the chain, which also speaks kind of for band formation. The longer you make the chain, you can actually figure out that there's intensity kind of stabilizing at specific energies. And this is really what we can understand in this simple kind of solid state example on how you actually create band structures. You start from 2 atoms, you add another one. Of course, you can have nearest atom neighbor interactions and next nearest neighbor interactions. And you can, of course, include it to higher orders. But the longer you make the chain, the more important, of course, gets the bulk of the chain. And this is how band formation comes across. And so here you have the energy in K-space. And of course, what we measure is kind of the von Hooft singularities. I'm almost at the end. So this is how we could get, in principle, these bands. We also see that they overlap with the Fermi level. However, what I should say that we did not find any signatures of this Majorana states.
1 minute.
Okay, so let me just summarize, or I just put up this. We can individually look at these U-Shiba-Rusinov states at single atoms. We can build up these chains and also create much longer chains. And with this, I would like to thank you for your attention, and again, the people who have actually done the work. Thank you.
Thank you very much for your nice talk. And if you have any question, we can have 1 or 2 questions. I think there is no question. And thank you very much, Professor Franke. I think we can move on our second speaker.
Thank you.
Thank you.
Hello.
Our next speaker, Burcu Çakırlı, and she's going to talk about empirical approach to nuclear structure and interaction and capture cross sections You can start, please.
It looks like I'm not able to, oh yeah, okay, maybe right now I can share. So, you see my slides, right?
There is no problem.
Are you able to see my slide?
There's no problem.
Thank you. And hello to everybody once more. Today, I am going to talk about, as you read here, empirical approach to nuclear structure with PN interaction, proton-neutron interactions, and neutron capture cross-sections. I'm a nuclear physicist, but some of you are not nuclear physicists. Therefore, I want to start my talk with a general overview with nuclear structure. With that subject, I will talk about nuclear evolution. I will talk about nuclear observables for even nuclei. We mostly talk about even nuclei for the simplicity. And during that time, I will also mention magicity, collectivity, deformation, so on. And at the end, I will briefly mention proton-neutron interaction and will connect it to masses. At that time, I will try to emphasize the masses, the importance of masses. Then I will show you some plots related to neutron capture cross-sections. And at the end, I will try to explain you a nice correlation between masses and neutron capture cross-sections. Okay, here I will talk about some experimental observables in nuclear structure we are using. For example, the first excited 2+ state, E2, or the R42 ratio. It's the ratio between the first excited 4+ state and the first excited 2+ state. And transition rates, here E2, electric quadrupole transition, gamma ray. It's a transition between, for example, from the first 2+ state to the ground state, which is which is valid for even nuclei. Always 0+ is the ground state. And these are some observables in nuclear structure. In addition, we can look at the radius of a nucleus. This is also very nice observable, and separation energies, which is related to masses. In this slide, we will see how nuclear structure is changing the structural evolution for even nuclei. Here, the shape of the nucleus is sphere. We have the case for double magic nuclei. So what's double magic nuclei? So if the proton number and the neutron number are magic, so it's a double magic nuclei. In nuclear structure, the magic numbers are 2, 8, 20, 28, 50, 82, and so on. If both protons and neutrons are magic, or one of them is magic, then the shape of the nucleus is sphere, and the first excited 2+ is very high. So what's very high? It's in MAB. It's like 2, 3, 4, 5, whatever. The R42 ratio, which is another observable, is less than 2. It's like 1.3, 1.4, 1.8, something like this. As soon as we have some valence particles, 2, 3, 4, or more, up to actually 4, maybe for this case, the shape of the nucleus is going to be changed, and the nucleus starts to vibrate. Okay. At that time, the first excited 2+ state is decreasing. Usually, for vibrational nuclei, the first excited 2+ state is roughly 700 keV, 600, 800, in that range. The R42 ratio is roughly, for vibrational nuclei, 2.2, 2.1. And when we go to more to the mid shell, So we have more valence particles, and there are many valence particles. That means there are many interactions between those valence particles. Then the 2+, the first excited 2+, is really decreasing much more, and it's going to be less than 100 keV, like 80, 70, 60. Then the nucleus rotates. In this case, it's the nucleus, the shape of the nucleus is ellipsoidal, and nuclei are well deformed in this case. So it's a mid-shell nuclei. The R4-2 ratio is as maximum 3.33 can be. So at the beginning of a shell, the shape of the nucleus is sphere. When we go to mid-shell, the shape is going to be ellipsoidal, 2+ is decreasing, R4-2 is increasing. After the mid-shell, if we go to the next magic number, so we see almost a symmetric case towards the next magic number, and we have almost the same results for the observables. So I mentioned the first excited 2+ state and the R4-2 ratio, and another observable, for example, BE2's transition strength, E2 probability. It's very low for magic nuclei in Weisskopf unit. It's like 2, 3 Weisskopf unit. And it's going to be large when we go to the mid-shell. So what's large? It can be like 200 Weisskopf unit, 300 Weisskopf unit, but it cannot be like 1,000 or so. Here you see 2D plot, color-coded. This is for the first excited 2+ state. This is for the R4-2 ratio for the same nuclei. And these plots cover almost whole the nuclei chart. Nuclei, it starts from 10, therefore I say almost all. The color code is changing from blue, which is deformed case for this plot, to spherical case. It's the same here, same meaning in the colors. So you can compare these two plots easily. There are two different observables, and if you compare these, in general, you see a very nice agreement between them, because we see dark blue colors around mid-shell. So maybe I can point out magic numbers here. Sorry, it's just a sec. And these are the magic numbers. And we have reddish colors around the magic number, spherical case. And when we go to mid-shell, so we have blue, dark blue colors, so deformed case. So you can compare these two observables. So what we expect is that we expect the same result by looking at different observables, right? And yes, we see the same kind of conclusion by looking at two different observables. One of the fascinating questions for the future is if these remarkable trends will continue in nuclei far from stability. So this is the main point by looking at such plots. Another observable is binding energies. Actually, separation energies, I said, but we cannot directly measure separation energies. We measure the mass, and then we can extract the S2N value. So what is S2N? S2N, 2N is 2 neutron here. This is a separation energy. So 2 neutron to separate. It is just an energy. And we can define this S2N with difference of binding energies between N and N-2 for 2 neutron. So the meaning is that how much energy you should cost to take out 2 neutrons from a nucleus, for example. So you can also look at S2P, 2 proton separation energies, or SN, 1 neutron separation energy, SP, 1 proton separation energy. So of course, binding energy formula is here. So this is also another observable I said. So what do we see? For example, we see the shell effect clearly in this plot as a function of neutron number. There's a sudden decrease in S2N just after a magic number here, 82. And here, after 126. So each line is one nucleus with different isotopes. So as a function of neutron number. So there's a shell effect which is seen clearly in this plot. And if you look at the plot more carefully, it looks like there's a linear trend, down linear trend, except maybe this region. In nuclear physics, this is a very well-known region, neutron number around 90. Shape phase transitions happen here, but I will come back to this point later. So by looking at S2N, we can understand shell structure, shell gaps, shape phase transitions. At least we can have a quick idea about the structure, and pairing effects by putting different filters using binding energies. S2N is one of them. And also we can understand PN interaction. So this PN interaction is called delta VPN, just here. It's shown here at the bottom, delta VPN. So delta is coming from the average, meaning VPN is the PN interaction. So what is delta VPN? Before I talk about it, maybe I can just mention why proton-neutron interaction is important. It's important because we can understand development of configuration mixing, collectivity, which occurs with many valence particles, deformation, magic numbers, and single particle energies and their change, so on. We can understand many things in nuclear structure by looking at proton-neutron interactions. So can we measure proton-neutron interaction? We can measure delta VPN because delta VPN is a kind of filter using binding energies. So if you look at here, just here, this is S2N. So it's like the difference of different two neutron separation energies. So this delta VPN is actually giving us an average PN interaction between only the last two protons and the last two neutrons. I'm not going to talk about this subject today. It's a completely different subject, but I'm trying to explain the importance of masses in nuclear structure. So if you don't know one of the binding energies here, for example, you cannot get the delta VPN result. If you use experimental binding energies here, you can get an experimental delta VPN result. So it's very important. So no time to explain about delta VPN because I will talk about a different subject. So I'm now going back to S2N plot again, but this is not the same as the one I showed you. This is for the rare earth region only, from neodymium to tungsten. So if you look at this figure, especially for these nuclei, you see this downtrend. It's like linear, except these points. There's a more binding here. And this is a well-known region, I said in one of the previous slides. And the shape of these nuclei is changing from spherical to prolate deformed. We know these. And if you look at this plot, again, there's a kind of downtrend. It looks like linear, right? So when you look at this plot, suddenly you may think, what is this? It's very similar as S2N. This is what we said. So what is this plot? The scale is different, yes, but the trend, the behavior, it looks like as S2N. But this is not S2N. This is neutron capture cross-section plot. Experimental neutron capture cross-sections as a function of mass number. So then you may think, so is this similar masses, S2N, and neutron capture cross-sections? Is it just accidental? Is it possible to have a correlation between them? So this was the main starting point for us to make the relation between masses and neutron capture cross-sections. So what is neutron capture cross-section briefly? A nucleus can get one free neutron, then we have a heavier isotope. So a free neutron can be observed, then you get a heavier isotope. So in astrophysics, I'm not an astrophysicist, by the way, but we know some basic information about astrophysics, this S process and R process. If I remind you, S process is a slow process. R process is a rapid process. The difference between them is just the time scale in terms of beta decay. So S process centers on stable nuclei mostly and near stable nuclei, and it just competes with the beta decay. But R process, it outruns the beta decay. Then you go to more neutron-rich nuclei in nuclei chart. You go to neutron drip line. So you go to actually isotopic region. Okay, then neutron capture cross sections are playing an important role in the predicted R process abundances. But since we are going to neutron-rich side in nuclei chart, that means the half-life of those nuclei is very short. So they are short-lived. Then we need cross-sections for them. So the question is this: if we know the S2N for those nuclei, can we get or predict the cross-section for those nuclei? So briefly, is there any correlation between S2N and cross-sections? We were curious about it, and we had this plot. So this is neutron capture cross-section experimental results as a function of S2N. For only deformed rare earth nuclei, about 33 nuclei, we had this curve and we had an exponential fit for these points, and we have this fit function. And it looks like we have a very nice correlation, stringy correlation between S2N and neutron capture cross-section. For example, if you know one S2N value, you can predict what is the neutron capture, just interpolation. It's easy. This is for 30 keV. So you may think, okay, neutron energies, I mean, not only 30 keV, there's a range from kilo electron volt to a few mega electron volt. So why did we use 30 keV? Okay, here you see the result for 30 keV, because best measurements are coming from 30 keV as far as I know. We tried the same kind of approach for different energies as well, from 5 keV to 100 keV. Of course, we can go to MeV, but in terms of the lab work, and also if you think of the neutron is just coming towards a nucleus, if it is very fast, then the nucleus cannot really get the neutron. The cross-section is very small. But if the neutron is slow, then the capture process can happen. The cross-section will be high. Therefore, in terms of the lab works, we have to stop at a certain neutron energy because it depends on 1/V. Therefore, we stop at 100 keV. So we chose 11 different energies in this range. And we didn't also look at only the rare earth region. We looked at different regions as well. 5 different regions, 7 classes of nuclei. So different regions through actinides. And we separated rare earths to 3 different regions, considering even Z, even N, even Z odd N or so. All the results are seen in this plot. There are about 100 nuclei on this plot and roughly 700 data points here. And this curve, this blue curve, is the same fit function as I showed you before. So it's the same. So it looks like all the nuclei are almost along the curve. So it's a very nice correlation actually between cross sections and S2N. There's one more thing I want to tell you. Maybe you can think about this. So I said different energies. In the previous slide, I showed you the results for 30 keV. So how can we have all of them in one plot? Okay, it's energy dependence. So what we did, so for each region, for example, actinides, the energy dependence of the cross sections was fit by an empirical curve, and that curve, using that curve, the data is normalized to their effective cross sections at 30 kV. So therefore, I used 30 here. Okay, therefore we see all of them. So there's a shift in the energy. Therefore, it's called effective S2N. Okay. So the result is remarkable, we think. So we do this approach with nuclear masses. It's actually very nice to have such an approach for me, because S2N is always a subject in nuclear structure. It's a structural property. We are talking about it all the time, especially for mass measurers are always talking about S2N. But for nuclear reaction studies, especially for neutron capture cross sections, S2N is not a subject as we always talk. So it may be a very common to talk about S2N in also nuclear reaction studies. So this is something new, and this was not recognized before. And as I said, I'm not an astrophysicist and I am not a theoretician. So there are many complex calculations in this stuff. I have no idea about them. But what I can tell you, for us, up to 100 kV, as I mentioned, we have much better accuracy than all the complicated theoretical results. So if I come back to S2N again as a function of neutron number plot, so I want to focus on again this more binding region, because we should understand how this can affect to the R process abundances. Then we focused on each nucleus. Before I show you this, so you can think of two questions here by thinking of what can be in terms of the R process. So what this extra binding can cause in the R process. So two main questions for this. Is this anomaly in S2N large enough to be visible in the cross sections? This is the first question. And the second question, is this large enough to have a clear effect on the R process? So therefore, we focused on each nucleus, and I will show you gadolinium results. This is blue triangle here. This is data. So this is an experimental result. I show you the fit function. Using that fit function and also this S2N, you can simply predict the neutron capture cross sections. This is for gadolinium. Using experimental S2N, and this is the fit function, we get this result. This is the prediction. So these are experimental S2Ns. So this effect, this more binding, is coming here like this. So right now, let's think that there is no more binding here. Let's assume this is just going down as linearly. So what do we get here? Like this. This is the result. So these black squares are coming from the experimental S2N values I showed in the previous slide. And these red points are from linearized S2N. The difference between them is roughly 450 millibar. So it looks like this non-linearity in S2N changed neutron capture cross sections roughly 50%. So here to here, it's double. So what do we understand? So S2N decreases then cross-section decreases. When the cross-section decreases, for example, when we go to short-lived nuclei, neutron-rich site, then if the cross-section is very small, then the beta decay will happen, the nucleus will change, the Z will change. Then abundance will increase. So S2N decrease, the abundance will decrease. We see more binding in S2N. So by thinking of not having this extra binding, let's say retarding decrease in S2N, what happens? Then appearance of the abundance peak will shift to higher A. So this is very critical to deduce our process properties from nuclear effects. And all should be, of course, considered to test the idea. So to test the idea, we need new S2N values, so we need new mass measurements. Here you can see the predicted neutron capture cross sections plus experimental cross sections as a function of neutron number. I mean, the agreement is really wonderful. So what do we expect more? This is the prediction plus experiment. They are very, very similar to each other. This is only for the rare earth region. We looked at different regions as well. The different regions, okay, I am just presenting here the rare earth region, different regions like the ones I showed you in one of the previous slides, 5 different regions, heavier ones. We mostly focused on mass number around 110 true actinides. So 5 different regions, 7 classes of nuclei. Then we have about roughly 200 something predicted neutron capture cross sections. So here you see only some of them.
You have 2 minutes, please.
So I am going to conclude my talk. So at the beginning, I tried to give you an idea how we can understand the structural changes in nuclear physics quickly, different observables I showed you. And then I said masses and nice correlation between masses and neutron capture cross sections I tried to explain. And we have some published papers on this subject. We are going to publish a longer one considering more regions I mentioned. So our results are showing plus minus roughly 25% accuracy. And lastly, I can simply say S2N, so mass measurements are very important to estimate our process abundances. So this will make a nice correlation, nice relation between different communities. We actually submitted a proposal to CERN a couple of months ago. It's accepted, and we are going to test the idea hopefully in a couple of months. I would like to thank my collaborators for this neutron capture cross-section study, Erin Couture from Los Alamos and Rick Kasten from Yale and Michigan State. And I would like to thank you for your attention.
For your nice talk, and I would like to get some questions if you have. Is there any question? Thank you very much, Dr. Çakırlı again, and we can move on our next speaker. Our next speaker is Sergey Odintsov. His talk about on the universe, unified history and modified gravity. Please, could you start? Thank you very much.
Okay, un momento. Just a moment. Could you please give me access?
Yes, we are hearing and we are looking for your talk, please.
It says that still Amphitryon didn't give me the access. Okay, now.
We are hearing. There is no
Yeah,
problem.
yeah. No, just a moment. Okay.
That's all right.
Now it's okay. Okay, it's a pleasure to give some talk here in this meeting of Physical Society of Turkey. I have been a couple times visiting my friends and colleagues in this very nice country, and it's a pity this time I could not come physically and should give, as most of us, the talk online. So in this talk, I will repeat on quite a simple level some introduction to new approach to the description of the universe history in frames of so-called modified gravity. So I will try most qualitatively, trying to avoid very complicated technical details to explain you what is the problem with the universe evolution now, what are the tools to describe this universe evolution currently, and why we are talking now about so-called modified gravity, actually about huge classes of different modified gravity. So let me start from the following point. For many, many years, since discovery of Einstein general relativity as the only viable gravitational theory, it was considered a priori that the only realistic gravity is general relativity. There were several different arguments for that, and the main argument was the following: that in the description of gravitational physics in solar system, we have several, let's say, so-called solar system bounds. First of all, of course, gravitational force, so Newton law, and several more. And it was repeatedly said that the only general relativity may pass gravitational tests of solar system. Okay, so in principle that looks nice, but recently, with the discovery in cosmology of inflation, so inflationary epoch some 40 years ago, and with the discovery of so-called current dark energy epoch currently, we see that there are the problems with general relativity, and I try to point out these problems and to describe how we can give much better understanding of universe evolution within modification of gravity. So that is big course of lections. I will talk mainly about some specific gravity, so-called FR gravity. But before I give some introduction. So I will describe now gravity-dominated evolution of the universe. The question is, why we may consider that general relativity is not enough and is not the only gravitational theory to describe the universe. I understand that not all of you, or mostly of you, are not cosmologists, so you don't know much about cosmology of the universe, apart from perhaps university courses. So let me give you very simple qualitative example. Imagine you calculate quantum effects, as you usually do in quantum field theory or in quantum condensed matter. For instance, you can calculate polarization, so vacuum polarization of quantum fields. Imagine that you work with usual, I don't know, QCD, even QED, or even quantum scalar field theory, and you calculate vacuum polarization, assuming that you work not in Minkowski space, but you work in curved space-time. So you work in expanding universe. In that case, when you calculate polarization and you consider that gravity is classical, usual general relativity, so you don't quantize gravity, you immediately see that they appear so-called high derivative terms. In communities, they are known as, for different version of the theory, or as conformal anomaly or vacuum polarization. So that high derivative terms, they appear in the form, for example, of R-squared terms. So starting from usual general relativity and supposing only one point, that quantum field theory is correct, and we know, because on our planet quantum field theory works very well, we know that quantum field theory is correct here, we immediately see that we arrive to another gravitational theory which totally differs from general relativity. If we consider quantum gravity, which is, despite of almost 100 years of very intensive work, is not constructed as theory, it may produce even more high order high derivative terms in gravity. So we are sure now that at the early universe, gravity was totally different from general relativity, because high derivative terms were produced by quantum field theory, and eventually they were modified by quantum gravity theory. They could even enter in non-local form, etc., etc. Then, if our gravity at the very early universe is different from general relativity, then the natural question is why such terms should disappear now? Why such terms should not play a very important role in the current universe? Why we only consider general relativity? The only answer currently is the following: because general relativity is good at solar system currently. However, I will explain that also modified gravity, so not general relativity, may be good in solar system currently. So the first point is quantum effects modify Einstein gravity. Next point, we know now almost undoubtedly that a universe passed the epoch of so-called early time inflation or early time acceleration epoch, where very quickly the universe expanded exponentially, and it came finally to its present huge size. Now, there are several hundreds inflationary models which suggest how we describe inflation. Most of them are based on the use of different scalar models with different potentials. So we should suggest some cosmological scalar. Of course, it may be also Higgs scalar with specific potential to describe inflation. And then somehow we should explain why this cosmological scalar is not seen at the current universe. It's somehow logically incorrect. However, we know that inflation may be described also by modified gravity theory. The well-known example of such inflation is so-called R-square inflation. So inflation which occurs in high derivative gravity with R-square term. The advantage of such inflation is that there is no need for cosmological inflaton, and there is no need for some fluid to describe inflation. We have very good agreement with Planck observational data in R-square gravity and in many, many other modified gravity theories, which perhaps I will show numerically in a couple slides later on. Next point is modified gravity may very well describe dark energy. Again, to describe dark energy, which is late time acceleration epoch of the universe, we need, at least at the beginning, some 20 years ago when this dark energy was discovered, we need some so-called dark scalar or dark fluid, so some exotic matter to describe this dark energy. And this dark energy is predicted by observation, so it's not our theoretician's invention. Okay? Then, if we describe dark energy epoch by scalar or fluid, immediate question is where this dark scalar or dark fluid was at the very early universe. Why it disappeared from there, or why it appeared just currently? That is quite complicated question, and again, we feel uncomfortable with this question. However, if we try to apply modified gravity, in simplest case, FR gravity theory, we can easily describe dark energy epoch up to the same accuracy as usual lambda CDM model. So that was first example of such theory. We can go further, and we can consider, can same gravitational theory be consistent and describe the whole universe history from the very beginning up to the current time. And indeed, we see that unification of early time inflation and light time acceleration in modified gravity is possible. So the first proposal of that time, of that sort, was given in FR gravity, but of course we have now many more proposals in different modified gravity, which are not only qualitatively but numerically well described unified inflation with late time acceleration in modified gravity. So we need no any extra scalars, vectors, spinors, etc. to explain inflation or dark energy epoch. However, the universe evolution changed the gravitational action, and then gravitational action changed the features of the universe history and induced the universe acceleration. So how it looks qualitatively? Qualitatively, we have, say, some terms in gravitational actions which describe early time universe. And these terms become negligible in current epoch. However, there are also some terms which are negligible at the early universe and which become important at current universe. That is, say, qualitative picture. Further step, we can go to complete description of the universe history from early time inflation via radiation and matter dominance to dark energy epoch within the same modified gravity. Again, we may propose already in the class of FR modified gravity, we can propose FR gravity, which is consistent with realistic cosmology. However, its form is rather complicated, so it's given in terms of some special function, and not very, there is no big pleasure to work with its form. However, one can work with approximated form of such theory. Important point is that in this case, we easily can include quantum gravity effects at the inflationary epoch, of course, when we know quantum gravity. Extra benefit of such approach to the whole universe evolution is that we also can include dark matter as modified gravity effect. So there are few possibilities, but already in simple FR gravity, we can include this dark matter. So we have, and this dark matter is mimicked by some composite degree of freedom of FR gravity. So we have inflation, dark energy in dark matter from the same modified gravity. Of course, I'm talking about quite simple modified gravity, which is quite remarkable because this theory, which is ghost-free theory, and that is important for consistency of such theory. Furthermore, I talk here using metric formulation. So in 90% of studies in cosmology currently, we consider that gravity theory is described in metric variables. So metric tensor is variable in such gravity theory. However, it's not the only approach. And since the time of Einstein, it's known that there is possibility also to use, to consider affine gravity, or so the theory where not metric tensor is variable in gravitational theory, but say where Christoffel symbols are variables. For general relativity, it does matter because both these formulations are the same. However, in modified gravity theory, already in FR gravity, we have difference in Z, and we have qualitative difference in such description. Nevertheless, I talk about only modified FR gravity in metric formulation. There are many proposals for modified gravity, so I'll give just several of them. So modified Gauss-Bonnet gravity, or FG gravity. So Gauss-Bonnet term is some combination of fourth derivative, higher derivative terms constructed of Riemann and Ricci square combinations, so that to get topological invariant in 4 dimensions. So if we add this topological invariant to usual general relativity, it does matter because it's just a surface term, and you may drop it out. However, if you add some function of it, it gives non-trivial contribution to cosmology, and the theory may be interesting because it enjoys by second order differential equations. We may consider non-local modified gravity. As you know, when you apply different approximation schemes in usual quantum field theory, you arrive to non-local terms. So similar motivation is for consideration of non-local modified gravity. So there are different approaches and different models suggested in this, but this direction is much less developed than FR gravity because it's complicated. Not to forget, we may consider string-inspired Gauss-Bonnet gravity. You know that string theory for nearly 50 years was proposed as a candidate for quantum gravity. Despite of many, many years of work, string theory did not succeed to become a really realistic quantum gravity candidate. Still, there are some hopes, and at least we can consider some low energy effective action from string theory, and kind of this is string-inspired Gauss-Bonnet gravity. Again, within such theory, which includes this topological Gauss-Bonnet invariant, we may achieve unification of inflation with dark energy. First example of that sort is given here. We may consider more proposals for modified gravity. So we have huge class of them. We may consider Born-Infeld versions of modified gravity theory. When we work with determinant gravitational theory, just similar to Born-Infeld electrodynamics, okay? This direction also works, but it's again complicated and not so much attention to it as to FR gravity. There are proposals on modification of gravity when it excludes non-minimal coupling of gravity with matter. Example of that sort is so-called RT gravity, where R is scalar tensor, tensor of scalar curvature, and T is a trace of energy momentum tensor. So there is some literature on cosmology from such theory. This interesting theory, and it's developed. We also may consider so-called direct coupling of curvature terms with whole meta-Lagrangian. So when in the action, meta-Lagrangian couples directly like R phi square term in scalar theory, non-minimal term, we may consider coupling of FR function with whole metal Lagrangian. That is also interesting approach which is developing, but still FR gravity is the main. There are also teleparallel gravity, FT gravity, where instead of metric we use torsion. There is vector gravity where we have vector tensors. There is massive gravity, but massive gravity has its own problems. There is Harave-Lifshitz gravity where Lorentz symmetry is broken. So we can continue this list of modified gravity theories. Why in say last 15 years there is so huge attention to different modification of gravity? The reason is very simple. We realized like how we can construct consistent gravitational physics in solar system within usual modified gravity. So now the claim which, for example, when I was student, was taught in the course of general relativity, that only general relativity successfully describe consistent gravitational physics in solar system is incorrect. Huge classes of modified gravity, most of the classes above or subclasses from the series above, and first of all FR gravity, do not modify Newton law and do not change gravitational physics in solar system. Of course, that is not so trivial fact, and it needs some description, some adjusting of classes of series, sometimes parameters of series, but that is the point. We have huge class of modified gravities which pass solar system test. Another very interesting possibility in modified gravity is that there is the possibility to realize unification of grand unified series with higher derivative gravity, like A-square gravity, and construct consistent quantum gravity with grand unified theory, which give you consistent realistic universe history. And with all this, of course, we have huge number of applications. For example, relativistic stars. When we consider relativistic stars, in usual general relativity, we have a lot of studies, realistic equation of states, a lot of restrictions. For example, let's take neutron stars. In neutron stars, we, some 20 years ago, about 20 years ago, we found some stars with solar mass of 2-3 solar mass and small radius like 7, 8, 9 kilometers experimentally, and all realistic equation of states from astrophysics to describe neutron stars do not work in this case. So there are problems to describe such neutron stars. However, if we consider such neutron stars in frames of modified gravity, we did a lot of study with FR gravity in this case, we see that it's possible to describe even this maximum radius neutron stars with large masses, maximum masses in terms of modified gravity.
You have 5 minutes, please.
Yeah. We have also wormholes, and wormholes are usually may appear only when we have some exotic matter, like phantom matter. Again, in frames of modified gravity, we have number of exotic wormholes. So if some modified gravity will be proved to be most realistic gravitational theory, we expect that wormholes will come from science fiction to reality. We have modification of black hole thermodynamics, and these modifications, they lead to a number of interesting stories. For example, we have a possibility for black holes in modified Gauss-Bonnet gravity to get negative entropy, which gives us number of questions and a huge field to think about generalization of black hole thermodynamics. So there are a number of reviews on modified gravity. So in couple last minutes, I just give several formulas to explain you what is modified gravity. Simplest modified gravity is FR gravity, where instead of usual term scalar curvature in action, we consider some function. We may write the equations of motion in different forms for such theory. We can introduce effective energy momentum tensor from modified gravity. Of course, that is just notation. Effectively, all these are high derivative gravitational terms. So we have, instead of usual system of two derivatives differential equation in general relativity, we have system of four derivatives differential equation in this case. Interesting that in this case, we have also the fact that even trace equation, which is trivial in case of general relativity, curvature is equal trace of matter, is non-trivial equation of motion, which gives us very rich dynamics. Important property of FR gravity and why it's ghost-free is the fact that it may be transformed by introduction of auxiliary field A to scalar tensor theory of this form. And sometimes the using of this scalar tensor theory simplifies the study of this theory. And by the way, it proves why this theory is ghost-free. Still, this equivalence is not physical equivalence because there are many examples like the study of singularities, black holes, thermodynamics, etc., where this series, even mathematical equivalence between these series is lost. So I have no time to give you explicit examples. I just give you one example of the theory where we may reach unification of inflation with dark energy. So we have usual general relativity term. We have the term which describe inflation. We have the term which describe dark energy epoch, and we have the term which describe exit from inflation and transition to radiation and matter domination. This theory in dark energy sector is completely equivalent by prediction to lambda CDM, and in inflationary sector, it gives inflation consistent with Planck observational data. So to finish, I just want that you remember that now there are very realistic modified gravity theories. That is one of the best of such theories, which describes the whole universe evolution from the early inflation till dark epoch. And of course, we should now work more on observational data to select which of this theory is most reliable, most realistic to more teeny effects. And that is one of the reasons why we currently study gravitational waves, which of course in such theories differ qualitatively from gravitational waves in general relativity. So let me stop on this point.
Your talk, is there any question, we can have it. And there is one question here.
Здравствуйте. I have a question about that Higgs boson, and if actually I asked that question another participants, and I'm curious that if Higgs boson gives that mass to particles, then can we measure gravitation with Higgs boson?
Okay, so Higgs boson is part of standard model theory. Okay, it's important for unification in QCD. So you can use Higgs boson for unification for description of inflation. For example, there were proposals that Higgs boson can give inflation. In that case, you have some restriction to mass of Higgs boson. However, that restriction are not so strict as, say, in standard model. So all restriction to parameters of Higgs boson you should search in standard model, not from gravitational side, because for gravity Higgs boson may be just kind of cosmological scalar which helps with inflation, because when it gives main contribution to inflation, we have extra problems. Why, for example, Higgs boson describes inflation but doesn't describe dark epoch? Why it disappears at cosmological level at dark epoch, etc., etc. So your question better to standard model physicists, not to gravitational physics.
Actually, I tried to understand that Newton's gravitation formula, then if there is G times M1 times M2 divided by R square, then if we take M1 and M2's Higgs bosons, then can we get our equation in this way? I thought that.
Okay. Newton gravitation we may describe without any Higgs boson. You need for that only gravity, nothing else. So why you need Higgs boson to describe Newton gravitation?
Actually, Higgs boson as a mass.
Okay, and what? So Higgs boson is not gravity, it's scalar field. So you do not want to have gravitation at all, only Higgs boson. How Higgs boson will describe your cosmology? So in gravity, it has additional role. So you should not be very serious about the role of Higgs boson in cosmology and in gravity theory.
Thanks a lot.
Thank you for question.
Is there any other question? There is no question. Thank you very much for your talk again. And we are going to have a coffee break for 15 minutes. And our next section is going to start 15 past 11. Thank you very much for your attention.
Hocam beni duyabiliyor musunuz? Buradayım hocam. Hocam birazdan yayına vereceğim. Çünkü şu anda bu ekranı görüyor Zoom'daki katılımcılarımız da. Tamam. Evet hocam edebilirsiniz ama sadece elinizdeki pointer'ı bu tarafa doğru çevirmenizi rica edeceğim. Çünkü alıcılar bu tarafta, perde kısmında değil. Evet hocam.
Bir de hocama bir mikrofon takabilir miyiz acaba?
Tabii bir saniye geliyorum.
Yapma şansı var mı? Hı hı, çok seviniriz.
Eko yok, tamam.
Sesimi alabiliyor musun? Tamamdır.
spontaneous polarization in the crystal. If you remember from classical electrodynamics, you polarize a crystal by applying an electric field to it. So you distort the positions of the ions and the atoms. Here, you don't need that. And well, there's another class of material. It's another ferroelectric transition, but this is what people call the antiferroelectric state. So the distortion happens in neighboring unit cells in opposite directions. And this is what we call the doubling of the unit cell because the period of the structure changes. So these have some specific phenomena that they exhibit. For instance, they exhibit a hysteresis in the electric field versus polarization. And the antiferroelectrics also exhibit this double loop structure, that's what we call. And this is in identical analogy with ferromagnets, where you have a ferromagnetic transition, or you might have an antiferromagnetic transition. With the development of the computational techniques, especially in the late 90s and early 2000s, so people started attacking the cause of these transitions. I mean, why a crystal would like to go from one symmetry state to another symmetry state based on the first principles calculations, and it's been shown for lead titanate and barium titanate. In fact, this is not even a first principles study. This is a detailed analysis of X-ray scattering, and then what they have concluded is that there is some covalent bonds and changes of ionicity with temperature that actually stabilizes such structures, both in lead titanate and barium titanate. So looking at these lead oxygen and titanium oxygen planes, it's about the, it's claimed that it's mostly about the hybridization. I mean, it's well understood now, again, like I said, with the first principle simulation. So there's also a quantum mechanical nature to it. Now, going to a more general continuum perspective, what happens is, like I said, we have a symmetrical phase, take it as a cube, and then transforms into a less symmetrical state. And it can now come in forms of variants. So you can have tetragonality in different directions in 3D. And and you can, in fact, measure at what temperature this happens and how these variants are oriented relative to the parent matrix. So this is the I'm going to go towards the Landau phase transition theory, but we have to first define an order parameter. So you can actually take the order parameter as maybe the strain in the system, or you can also take it as a polarization. It has to be something that you can access with experiment. And what happens is, so at high temperatures, you're in the cubic state, and at some critical temperature, you suddenly switch to a tetragonal state, and then the polarization, if this is polarization, so you have a suddenly appearing finite polarization, which then evolves smoothly with temperature as you reduce temperature. And one of the footprints of such a transition in the experiments is, if you look at the XRD, you have the cubic peak here, which is this dashed line. And then at this critical temperature, you have suddenly this peak splitting. And the reason is because of the structural variants. So this is, I think, for the 002 peak of the perovskite oxide, barium titanate. And they also reveal themselves as these very beautiful, nice patterns in the transmission electron microscope, where we have these elastic variants. I call them elastic variants because it's at the end of the deformation. And then these can reveal themselves, and each variant has its own polarization direction. They can reveal themselves in the diffraction contrast mode if you work with a TEM. Just some basics. So we say that the bulk ferroelectrics display a first order transition. And what is a first order transition? The order parameter, I mean, the new state appears abruptly, okay? And what's a second order transition? Well, in the second order transition, the new state appears very gradually. For instance, a ferromagnetic transition is a second order transition, but the ferroelectric transition in bulk is a first order transition. And well, when you cool sufficiently, both systems in fact display the hysteresis. And if you go to the Landau description of this phenomena, what Landau did was he just took these two terms, which implied the transition from a cubic state, which has a 0 order parameter. So let's say the polarization is 0, and then as you cool it down, then you get to this double well potential where the system, which is denoted here as this red ball, rolls into one of these states, which are degenerate states, and only these two terms, the p squared, p4 terms, are sufficient to describe it. The first term, the alpha, has a temperature dependency, and while this doesn't explain, so the Landau theory has to be modified to be able to account for the first order transitions, and then this is where the 6th power term comes from, because when you have this, and if you minimize this equation, then what you get at the transition is this green curve, which has 3 minima, because in a first order transition, as classically, what we know from thermodynamics of phase transitions, the two phases at the transition temperature has to have equal energy. And if you see, you have 3 minima, which have all the same energy. So I'm trying to continue fast. What happens? Well, everything I discussed now was valid for bulk transitions, which means it's a stress-free, visible, maybe crystal that you can play with in the lab environment. As with many other systems, with the development of these integrated circuits and all that, people are now interested in growing these ferroelectric films to tailor their spontaneous polarization in device applications. So when you talk about devices, you're talking about thin films. So what happens when if you can synthesize, if you can grow a ferroelectric crystal on a substrate, the entire picture changes. And the reason is because the substrate puts a severe elastic constraint on the film, and the film now is not free to just deform and form its polarization and variance freely. And there has been studies on this by especially the group of Partsev, and so they have generated these phase diagrams like you see here. So there's a pole domain state where there are variants which are periodically aligned in order to accommodate that volume change, because when you have deformation happening in your sample at the transition, then that means you have volume changes. But in the presence of the substrate, you are not free to change your volume as you want. So that's why the film decides to form some type of a pattern of variance. And the temperatures of the transitions change dramatically. And they also start exhibiting some interesting dielectric constants. This is just one example. It also applies to pyroelectric constants, piezoelectric constants, so which the ferroelectrics are also famous for. Another peculiar thing that we published in 2016 was the change in elastic constants, because if you can write the free energy of a system, and if you minimize the energy of the system, imagine the polarization existing with all this elastic energy that's accumulated in the structure. So if you can minimize this with respect to the strains, what happens is you find a very interesting, you come across a very interesting outcome, and that is the elastic constants can actually go negative, which, in our regular universe doesn't happen. I don't know, maybe it happens elsewhere, but on Earth, we never have negative elastic constants. So this has to be explained, and this is what we give here. Well, this is kind of like an isotropic approximation, but at least if one of the elastic constants, take the bulk modulus, which is a measure of the compressibility of the system, it goes negative near the transition, which is an impossible thing. So now we run into a dilemma. So how can you explain this? Near the transition, if you assume all these things happening, well, you have a region where you have negative elastic modulus. I'll come back to that. So that's one peculiarity about the transitions in thin films. Well, in our group, we are able to look into these things by means of computer simulations using the continuum media approximation and thermodynamic theory. So this is a nice, I think, example of how these domains, so cross sections. So these yellow regions are the regions where the polarization is pointing upwards, and The blue regions are the regions where polarization is pointing downwards, and these green ones in between are the variants that are pointing along the plane. So this is some type of a configuration that the film forms to accommodate the volume change. And so this has been considered as grown on a semiconductor. So it's called a semiconductor ferroelectric metal structure. And if you apply a bias on the top electrode here, then you start seeing the domains evolving. And well, this positive bias tries to actually switch the up pointing regions, tries to change their sign. So we have all these blue regions, but at the same time, you see that the in-plane variants, which are pointing in parallel to the interface, are also growing. So this is something we can simulate. So we can check with the effects of electrostatics and elasticity. And why domains are important? Well, two nice examples that might be of interest to the condensed matter physics community. For second harmonic generation, you need phase matching. You need some periodicity in the crystal structure to make the phase matching. So these domains actually help with second harmonic generation. You have some periodic perturbation in the structure. And relatively recently, people are now replacing the top metal electrode with graphene and trying to benefit from these domain structures to control with applied bias how, for instance, terahertz plasmons would propagate. So you have these tunable terahertz devices that are possible. The most famous application of the ferroelectrics is about the solid state memory. So all these hard drives that we have in our computers are based on ferromagnets. So you have magnetism pointing in one direction, it's say 0, pointing in another direction, it's 1. And then how you read it, well, you have the GMR effect. So if you have two parallel or anti-parallel states on a head, then that actually changes the resistance, and that's how you read the data on your hard drives. Well, now people want to go towards more solid state memories where you don't have any moving parts. So everything is digital and electronics, and ferroelectrics come forth in the pursuit of such devices. One example is here, for instance. These are transistor architectures where the gate oxide is replaced by a ferroelectric. And because the polarization points up or down can actually create different conductivities in the superconducting channel. So this is one thing. There is also this, there's a number of device configurations that people have been proposing to incorporate ferroelectrics into semiconductor-based devices. And there's another one here, for instance. And what happens is with the current between the source and the drain. So this is kind of like a MOSFET architecture. So you have the, okay, well, I thought I had some few details here, but anyways, so you actually can go between, for different gate voltages, you can have this hysteresis, which people use for data storage and processing. So the channel state can be controlled and retained with the ferroelectric data, which puts the memory capability to your MOSFET. Another classical type of a memory setting using a ferroelectric is the capacitor type memory element. So this is the simplest. So you have two electrodes sandwiching a ferroelectric layer. In this case, it's PZT. PZT is lead zirconium titanate. So it's a solid solution, which also has ferroelectricity. And then we have the hysteresis of the ferroelectric. So what's it? It's electric field versus polarization. So you can go back and forth between up polarization and down polarization states. One of the challenges here was, okay, if you write a state, let's say up as 1, and then you want to read this. Now there's a whole story to it, because reading the data in the first proposed ferroelectric memory devices was what we call a destructive readout. So what happens? You have the polarization, you apply an opposite electric field. Well, you apply a reference field and then see how the capacitor is going to respond to you. So let's say the polarization is pointing up, you have no idea where it's pointing. So you apply the field, and if the polarization is in the opposite direction to your applied field, it switches. I mean, if the field is strong enough. And during the switching, then you have displacement current because you're moving the carriers from one electrode to the other. So if you can measure the current, so there's this thing called displacement current. And then when you read the displacement current, you know that the polarization was pointing in the opposite direction as your applied field. So now you keep that in mind. And well, okay, then you read your data, you know which way it was pointing, reference to your applied field. The applied field is always the same, in the same direction. But then because you destroyed the data, then you have to actually rewrite it again. So then you apply an opposite field, and now you restore the information. Well, this is power consuming. So now people are talking about non-destructive techniques, which is, I think, one of the next slides. But this was the traditional approach to storing data on a ferroelectric memory. Okay, well, memory, electrocaloric cooling, so I'm not going to go into much details here, but the same device, the same capacitor actually can also generate some significant temperatures, not because it has resistance to electric field or whatsoever, but because when you apply an electric field, you are inducing order in the system, which is changing the entropy of that little device. And then that excess entropy is given to the lattice, so it heats up. So, and if you can remove that heat and then remove the field, then it wants to go back and then needs this entropy back. And where is it going to get from? It's going to get from the lattice. And then in the experiments, you see that the lattice cools down. Okay, so this is the electrocaloric effect. So it can be put in a cycle like this, and it has to, again, with the traditional thermodynamics relations from the Gibbs energy, we have the coefficient relations. And then if we assume an adiabatic process, the process is so fast that it doesn't exchange any heat with the environment, you can assume. And then if we rearrange, so we can actually compute the temperature changes. Now, why are ferroelectrics important for ferroelectric cooling, electrocaloric cooling? Because there is this term here, which is the pyroelectric coefficient. And I just mentioned that these crystals, ferroelectric crystals, have the highest, some of the highest pyroelectric coefficients that we know of in materials. So that's why they are very attractive candidates for electrocaloric cooling in a simple capacitor setting. Well, again, so what people have done, they have constantly repeated what others have done. For instance, some group does magnetic superlattices, then some other group takes semiconductor superlattices, and the same tradition continues. So what people do, they just take then different ferroelectric layers and make these ferroelectric superlattices. These are alternating layers. And so these are, well, these are for the GMR effect, tunable optoelectronic devices. And then these systems show a lot of interesting properties like a giant pyroelectric response. The same system of superlattices have become important for this recent phenomena, which is negative capacitance, which has to do with the reducing of the energy in the way that the these MOSFETs function. So there is some interesting assumptions about that. If you obtain negative capacitance, then you can actually reduce the limits of the MOSFET voltages. Now I'm going to skip because I think I did spend too much time on the fundamentals. So the ferroelectric polarization when interfacing a semiconductor which has strong spin-orbit coupling, it can in fact change the characteristics of the spin-orbit coupling phenomena. Tunnel junctions, I mentioned about this destructive technique. Now people have proposed, I think in 2002, Korstedt and Wasser from Germany proposed this memory or non-destructive readout memory, which is based on the tunnel junctions and resistive memory principle. So this is kind of where I'm going to discuss our research. I'll try to conclude in 5 minutes. So what's the resistive memory? So the resistance of the system depends on some instantaneous moment that you're in. And this has to do with, for instance, in the regular resistive memories, how your vacancies, your defects are distributed. So you're actually in a dielectric benefiting from the presence of defects. And the same can be done with the ferroelectrics. So this was one of the motivations that we had. So we grew some films. and check their structural qualities. We formed some configurations for electrical measurements. We also in parallel carried out simulations on this model system here. And so what we saw was, I think this is the important one here, just to save on time. So we get these hysteresis in the current voltage measurements, which has to do with which way the polarization is pointing. So we have a bad capacitor, bad leaky capacitor, but that bad leaky capacitor, the polarization direction, in fact, determines whether leakage current flows more or less in a given direction, which is what we did in our simulations. And we were able to explain that this state 1 here that we saw has to do with the low resistance state because we don't have any carriers. So this is kind of like a charge map. And the state 4 is when the polarization is pointing down, which we had the entire capacitor, the ferroelectric layer flooded with carriers. And we were able to explain that based on the numerically computed flat band energy diagram. So when your conduction band in the ferroelectric, which is far from the valence band, well, if it enters into the Fermi level, then you get population in the conduction band, and that is the low resistance state. So I'm really speeding up here now. So I'm going to skip this. Well, I talked about transitions in thin film, so it's a transition in constrained media. And what happens is, again, you have the low symmetry state, but when you're clamped, you don't have the entire crystal switching to the new phase, and you can get these nice patterns of these low symmetry, high symmetry phases. Is it only in ferroelectrics? No. In vanadium oxide, for instance, it's another interesting material. It also has this type of patterns that it forms, for which people have computed these phase diagrams, like metal insulator transitions occurring as a function of elastic coupling and temperature. Yeah, so I'm gonna skip these. So what we decided to do, we said, okay, if the transition cannot proceed abruptly, well, it can proceed with phase coexistence. And what's the significance of this? The significance of this is if you know the van der Waals isotherm, the van der Waals gas, for instance, if you know, at some critical volume pressure region, well, you start getting into a region where you have negative compressibility. What is negative compressibility? You shrink the, you increase pressure, the volume wants to grow. So there's no such thing. And a similar, qualitatively similar thing is also happening in the ferroelectric. So you actually enter a negative elastic constant regime where the system will choose to exist in a phase coexistence. That happens in carbon dioxide, for instance, at some critical temperature and volume. You have this coexistence of the gas and the liquid. So well, we did some calculations. It was a simple system, one-dimensional system, which for which we wrote the Landau equations of minimization, and we were satisfying the equations of stress with the boundary conditions, and we did elastic analytical solutions using the results from a paper of Falk, and get these profiles, which then we also checked with the numerics because analytical approximation, well, analytical solution needed some approximations, and then we had to also do the numerics. I don't think it's clear here, but we were able to find these profiles and then go between, you know, which one is equilibrium, which one is metastable, and generate these type of phase diagrams where you have the high symmetry phase, you have the phase coexistence region, and then you have the low symmetry phase. So this is a new contribution to the literature, and it was published, in fact, this year. For a one-dimensional system, we are repeating the same results, repeating the same calculations for two-dimensional and three-dimensional case, and now we get some nice, interesting patterns at the transition. So what this means is the high symmetry phase that is stable above the critical temperature. In the case of elastic clamping, when this film is on a substrate, it can actually be stabilized all the way deep into the region where you have the low symmetry phase stable. So with that, I think I'm going to conclude, not to take more of your time. So this is, so the thing here is people assume that the transition becomes a second order transition in thin films, but we show that no, it cannot, because then runs into these difficulties with negative elastic constants and all that. So we are proposing that there's a phase coexistence that should happen. So the transition still remains first order because you have regions where the order parameter appears abruptly. And well, it's a difficult thing to do with experiments, and because it's a fundamental question, so doesn't affect much what happens at room temperature. So this is probably the way to conclude. So thank you very much, and I did exceed my. No, okay. I think.
Thank you very much to Professor Mısırlıoğlu for this nice talk. If you have any question, we can have it. Is there any question?
Thanks a lot to your presentation. And I have a question about transition. What's that? How is entropy during transition process? Can you explain a bit?
Yeah, well, so the, okay, in the most traditional sense, the entropy is the first derivative of the Gibbs energy. And so I don't want to, go into like a more qualitative description, but probably it's the best to understand. So the first derivative of the Gibbs energy gives you entropy. And because different phases have different Gibbs energies, so when you have a transition, then you have a change in Gibbs energy. And then what that gives you is a change in entropy. But if you ask from a more qualitative perspective, well, so your atoms, your energy states, your configurations, so all these things, when you're going through a transition, they are suddenly, changing. So the positions are changing, the electronic structure is changing. So all these also mean that your order is changing. So if your order is changing, that means your entropy is changing. So then you have these, it's a very clear sign of a transition, but you cannot measure entropy. It has to, it's linked with heat capacity. So entropy is an abstract phenomenon, but you can check the heat capacity, and then from there you can go to entropy. So this is probably the best explanation I can give you here now.
Thank you very much. Another question, we can have one more if you have. Otherwise, thank you very much for your nice talk again. Our next speaker is online, and he's from İzmir Institute of High Technology, and Professor Tuğrul Senger. He's going to talk about excitations in lead halide perovskites. You can start, Professor Senger.
Thank you, Professor Chairman. Hello, everyone. Let me share my slides. Okay, I hope it's available to you now. Okay, first of all, first of all, I would like to thank the organizers for inviting me for this Congress. My name is Tuğrul Senger, and I work at İzmir Institute of Technology. And here is the position of the campus. For those of you who are not familiar with geography of Turkey, we are at the very west end of Turkey in İzmir, and our campus is kind of outside the city. It's a nice, peaceful campus to work, and to do good science. The topic I'm going to talk about today is perovskites and the excitonic properties. And this is somewhat a new topic for my career. 2 years ago, I just spent my sabbatical year in UC Davis in California. It is a nice campus town in Northern California. And the problems that I'm going to talk about today have been studied in this physics department, as seen in the pictures. So I'd like to acknowledge the Fulbright Commission, which made this sabbatical visit possible. And of course, the host, Professor Dong Yu in UC Davis, and his kind of large research group there. So the experiments, the measurements that I'm going to show you today have been done by the group members of Professor Yu. And we had some collaboration for the synthesis of samples from University of Wisconsin, and also some theoretical input from Molecular Foundry by Liang Tan. Okay, so this is half an hour talk, so probably it doesn't need a short summary.
With internet.
Hello again. Okay. I'm sorry for the disconnection. Is it okay now?
Yes, it is okay. You can carry on, please.
Okay, I don't know the exact point where the connection was lost.
We are
Okay.
hearing, there is no problem, Professor Sanger.
Okay. Let me show the acknowledgement again. So I'd like to thank the Fulbright and the local host group there in UC Davis. And the problem I'm going to talk about today is the local excitation of a perovskite material, metal ammonium lead iodide, by a laser, and the diffusive characteristics of the carriers created by this local excitation. The excitation creates free electron hole pairs and also to some extent excitons, the bound pairs. And I'm going to show that we see large diffusion lengths for these photo-created carriers. And I would like to claim that those large diffusion lengths are due to the exciton formation, which is more mobile than the free carriers, electrons or holes, which have some polaronic properties. So this is the short summary of what I will talk today. So in order to...
I'm really sorry, Professor Senger, could you share your slides, please?
Okay. I thought I shared it.
You are not sharing still.
I'm trying to connect. Just a second.
Now it's okay.
All right.
And
Is it
that's
okay
all
now?
right. You can carry on.
Okay, so here's the outline. I'm going to give a very brief information about the material, lead halide perovskites, why they are interesting. And then I'm going to discuss the methodology, the scanning photocurrent microscopy to characterize these materials. And I'm going to show you the long carrier diffusion length measurements in this material. And then I will present some model and understanding to this finding. So perovskites have been quite popular in the recent decade, basically due to its efficient use in solar cells. So they are very promising and quite efficient in solar cell construction. And due to that, there has been quite a large interest in these materials. Well, to have a good solar cell, in fact, we need efficient conversion of light energy into charge carriers. This is one of the requirements. And the other requirement is that those carriers should be collected away from where they are created. That means we need high diffusion mobility for these carriers for efficient solar cells. And these perovskite materials satisfy these properties. The composition is, the general form is in this form, ABX3, where A is either an inorganic atom, or it could be an organic molecule like methylammonium or formamidinium. The B is always lead in this class, and the X represents the halide atoms, chlorine, bromine, or iodine. So in this talk, I'm going to talk about this methylammonium lead iodide material, which is usually called as MAPI in short. These crystals, MAPI crystals, are synthesized by using spin coating method. The solution is dispersed on the substrate, and then it's rotated and heated so that the constituents just create well-defined crystals on the substrate under appropriate conditions. And this is an SEM image of the final product of this process. You see some well-defined crystals in the form of bars, microplates, and with very clean facets and smooth surfaces. So we take those crystals and produce some devices. In case of MAPI and for the other members of the family, we have different crystal phases of this material. As a function of temperature, they experience either cubic, tetragonal, or orthorhombic phases. The crystal structure changes, and in particular, those organic molecule, which is the blue dot here, experiences different environments in different phases of the crystal. In this case, for MAPI, the second phase transition is above the room temperature, and we characterize our samples in the range room temperature to lower temperatures down to about 80 Kelvin. So we just see two phases of this material, tetragonal and orthorhombic. Those crystals produced in that way are transferred on to the substrates, which has two gold electrodes. And this is a very gentle process. Actually, we just carry those crystals by what we call cat hair transfer. We literally use cat hairs and use them like chopsticks to take those crystals and place them on the electrodes and gently push them towards the electrodes so that we have a transistor-like geometry for the device. And we characterize those devices by using scanning photocurrent microscopy, which is actually given in this cartoon. The crystal is excited locally by a laser. Let me run the animation also. So the laser quickly scans the sample, and at the same time we collect the current from the electrodes. There could be some source to drain potential, and also the gate potential can be applied to manipulate the device. And the samples can be arranged in a rather wide temperature range from 400K to down to 6K. This is our setup. So using this setup and device geometry, we produce some photocurrent maps. The current measured for a given excitation position, okay, we produce some two-dimensional maps, color maps of this sample. And as you see here, the red color corresponds to higher currents, and down to blue, the current is lower. At this temperature, this is what we observe as the photocurrent map. As you see, if you excite the sample close to the collecting electrode, you create a large photocurrent. In this case, there is no source drain voltage. Therefore, this current is produced by the diffusion of the created carriers to the electrode. So the source drain potential actually creates some electric field in the channel, but not outside, ideally. And there is also a bending property due to the connection of a semiconductor with the metal contact. And by that, we can actually switch the current peak position to which electrode we are going to observe by changing the polarity of the potential at the source drain. This is just an example for that. So we would like to determine the diffusion length of these photo-generated carriers. The way to do that is to obtain these curves, current curves, as a function of position. You see that there's an exponential drop of the current away from the electrode, as expected. And from this exponential fit, we determine the diffusion length for these carriers. I'm going to show you the temperature-dependent variation of these photocurrent maps first. At higher temperatures, close to starting from room temperature in the tetragonal phase, we see that the diffusion lengths are quite short, about 10 microns. But when you lower the temperature, then suddenly you see that there are photocurrents that are obtained even if the sample is excited away from the electrons. That means the diffusion length for the carriers is much longer at lower temperatures. In the orthorhombic phase, we see a sudden increase in the diffusion length of the carriers. So when you look at the crystal structures, when you go from tetragonal phase to the orthorhombic phase, the diffusion length of the carriers starts to increase rapidly. We can associate this with the crystal phase change by this measurement also. We see when you illuminate the sample globally, we see that the photocurrent just changes abruptly at the temperatures close to the reported phase transition. Since we have microcrystals, the phase transition temperature is a little bit lower than the 165. Okay, so this is due to the phase change. Here we see in this plot, you see the diffusion length variation as a function of temperature. So below the phase transition temperature, the diffusion length increases from about 10 microns to about 200 microns at 80 Kelvin. So how can we understand this? How should we interpret this long diffusion length at low temperatures? Well, it seems that it is possible by introducing the concepts of polarons, excitons, and polaronic excitons. I'm going to briefly show you these. The polaron is the interaction of the electron or hole with the ionic medium, which is the case for this MAPI. The electron distorts its environment, therefore its effective mass increases and its energy is now not the band energy, but the polaronic energy lowered by the interaction with the phonons, optical phonons. For MAPI, this interaction constant alpha is somewhat intermediate to large value, 2 to 3. Therefore, these electrons and holes in MAPI are in fact polarons, not band charge carriers. And their interaction with the LO phonons affects their diffusion properties dramatically. On the other hand, the exciton, which is formed by the Coulomb interaction of electrons and holes, is a neutral particle in terms of electric charge, and its interaction with the phonons is due to its dipole moment only. And the binding energy of the excitons in this material is again temperature dependent and the phase dependent. This is a recent experimental determination of the binding energies. The high temperature exciton binding energy is about 10 millielectron volts. On the other hand, at the low temperature phase, it's above 20 millielectron volts. So there's a sudden change in the binding energy of excitons.
You have 5 minutes, please.
Okay, I'm going to wrap it up. The polaronic excitons, the excitons formed by these electron and hole polarons, have some non-trivial properties. They have their polarization field just partially cancels. Therefore, the interaction of the excitons with the phonons is considerably reduced. So our hypothesis is this: these polaronic excitons interact much less with the ionic crystal lattice, and they can move much more easily than electrons. So I'm going to skip the calculations, but the polaronic excitons can be quite successfully dealt with the methodology of Polman-Büttner. Here is the Hamiltonian, so it gives us an effective potential by calculating the total energy and effective mass of the exciton in the presence of phonons. One can reproduce actually the exciton binding energy quite successfully with this model. So I'm going to pass that quite fast, but this is the result. When you see the binding energy in two different phases, we just expect quite reasonable values with the experiment, about 10 millielectron volts in the high temperature phase and about 20 millielectron volts in the low temperature phase. So I'm going to use these parameters as coming from the experiment and also from the calculation. So by this introducing this binding energy change in the phase transition, it can be summarized as here. It's quite evident that there are much more excitons in the low energy phase. All right, the binding energy exponentially determines how many excitons are there, bound pairs, as a function of temperature. And with the increase of binding energy, you see a sudden jump in the number of excitons present in the crystal at lower temperatures. This is one part. And the other aspect is these excitons are also more mobile than the polaronic free charge carriers. So the interaction of the exciton is through its induced dipole with the LO phonons, which is given like this. And if I compare the scattering rate of a free polaron and an exciton with the phonons, I see at least 1,000 times reduction in the scattering rate. So that means the polarons, the free carriers, are in fact not that mobile. They're quasi-particles, they're polarons, and it's like a quasi-horse, if you like. And exciton is a particle which is got rid of its interaction mostly with the LO phonons, and it became a real horse. So that is much more mobile compared to the electron or hole. So this is just a rough estimation, but it's quite dramatic. So therefore, when you combine these two facts, more excitons and more mobile excitons, you can extract this long diffusion length observed in these materials. So here is the explanation. We expect more excitons due to the larger binding energy, and we expect them to be more mobile. I'm going to skip this part, but in order to support this model, we have also performed numerical simulations based on these assumptions. All right, we modeled all the processes of excitons converting into free charge carriers and the recombination rates, etc. So we have solved some coupled differential equations in this manner. I'm going to, and using the appropriate parameters, which gives us the quite expected results. All right, so if you look at the cartoon, the free unbound carriers can be represented as snails as compared to the excitons that are represented by a rabbit. They are much more mobile. Okay, a few slides showing the details of the calculation, which I will omit. And you see here the comparison with the measurements of the diffusion length with the calculations. It's quite impressively, this green and blue curves are quite in agreement as a function of temperature. So the summary, is MAPI microcrystals show large carrier diffusion lengths at low temperatures. And we suggest that highly mobile excitons can explain this measurement. And we show a model in the detailed balance of polarons and polaronic excitons, which gives us a reasonable picture for the observed large diffusion lengths. And once again, I would like to thank my collaborators and thank you for your attention.
Thank you very much for your talk. And if you have any question, we can have 1 or 2 questions. There is no question. Thank you very much, Professor Senger, again.
Thank you.
We can move on our next speaker. And it's my great pleasure to introduce Professor Şener Oktik from Kadir Has University. And the title of his talk is on nanotechnology on the photonic energy conversion. You can start. Thank you very much.
I do thank you to Professor Çapan. Hello, everyone. This is the talk just one before the last one, so you're close to. Can you hear me? Hello?
Professor Şener Oktik, we are hearing, there is no problem.
Okay, I think I lost you. Hello again to everyone. This will be the talk one before the last one. I really thank you very much for joining to this talk. And also I'd like to thank Turkish Physical Society for the continuous effort over the 37 years to really hold these conferences, this Congress, to get us together to share the information. My talk today will be mostly on the review nature to give you some new idea, new area, new appetites for the new researchers. Shall I share my screen, please? Yeah. I cannot share my screen.
Share it.
It says only host. Could you really give me the authority to share the screen?
You can share it. There is no problem.
It says only host. So I'm not a co-host to be able to share my screen.
Okay.
You should really authorize me to share the screen.
Shall we give him host, please?
I should be the co-host. It's not allowing me to share my screen.
Arkadaşlar, hocamı
co-host yapabilir misiniz? Arkadaşlar, co-host yapabilir misiniz?
Hocam, şu anda her şey normal gözüküyor internette. Hocam paylaşmanız için bir engel gözükmüyor burada.
Okay, I will try. Where is my screen? Can you see the screen now?
Yes, we can see it. There is no problem. Please carry on. Thank you very much.
Thank you very much. Today, I will be talking on nanotechnology and photovoltaic applications. It's an area which will be really promising for the photovoltaic sector. Previous speaker already really mentioned perovskites and its potential. Today, what I will try to really go through in a review manner is selected milestones in nanotechnology and a brief summary of the current facts and figures of photovoltaic energy conversion. Of course, nanotechnology and photovoltaic energy conversion, I will try to show you some interesting examples on the crystalline silicon photovoltaic cells and nanotechnology applications. Also, there are significant effort and significant promises in nanotechnology and organic photovoltaic cells. And I will end up with some appetizers just before the lunch. The current, which is 2020, will be a selected research globally, who is doing what and what sort of efforts on applications of nanotechnology in photovoltaics. This is my disclaimer. My disclaimer suggests that this presentation contains the material just selected for this presentation. No one, including me, is not responsible in the outcome. Okay, when you say nanotechnology, one should start with, of course, big man Richard Feynman. Richard Feynman in 1959 said, there is plenty room at the bottom. What he meant was, manipulating matter at atomic level has a significant potential for understanding physics, chemistry, and the nature. In 1974, the first time Naruo Taniguchi used the word of nanotechnology and described the term processing, separation, and consolidation, and of course, the formation of materials by one atom or the molecules. Then when you really develop a new experimental techniques like scanning tunneling microscope in 1981, it opened really more way to understand. In 1981, there was a discovery of nanocrystalline semiconducting quantum dots in glass matrix. In 1984, there was a big discovery on the fullerenes and fullerene derivatives by three scientists. Actually, this ended up with the Nobel Prize in 1996. Those who are not in chemistry, probably I should say a couple of words in fullerenes. Fullerenes are the carbon molecules. If it's closed cage, like a football, it's called buckyballs, or fullerenes could be cylinder shape like carbon nanotubes, ellipsoid tube, or many other shapes and sizes of carbon combinations. Of course, one really needs to mention discovery of a semiconductor nanocrystallized quantum dots in 1985, and atomic force microscopes invention of this technique was again another pushing forward for nanotechnology. In 1989, IBM managed to put their own logo using just xenon atoms, as you can see in this figure. After that, the industry started getting interested technologically, and there are many companies working after 1990s rather, working on nanomaterials. Then, of course, one big step was synthesis of controlled doping of polymers. This was again a Nobel Prize in 2000. By that, scientists managed to really produce controllable organic conducting polymers, organic semiconductor polymers, and organic insulating polymers. And 2004, they discovered a new class of carbon nanomaterials, less than 10 nanometer carbon dots. Okay, the last 2 decades, nanotechnology start really moving from academic benchmark to the everyday products. Now we know nanotechnology is everywhere. The global market in 2020 was about 42 billion US dollars, and it's projected to be 70 within 5-6 years. Okay. When we say nanotechnology, actually also people really classify 3D materials. All the dimensions are bigger than 100 nanometers still in this group. But when you say nanomaterials, you are talking about nanoscale, which is less than 100 nanometer. The 3D materials, there are several applications as listed in here. And there are, of course, 2D materials. In this, only one dimension is at nanoscale, the other one is quite large. What are they? For instance, anti-reflective coating windows for phone, solar cells application, touch screens. You can really see all those applications using nanoflakes, nanosheets, or nanofilms. 1D materials, nanowires, nanotubes, nanoribbons. As you can see, they also found significant application in industries. And of course, zero-dimension materials or quantum dots or nanocapsules or nanoparticles have applications in surface coatings, cosmetics, sunscreens, antibacterial. You can think of anything, you can find some zero-dimensional nanomaterials. Okay, back to the actual subject. If we are talking about nanotechnology and photovoltaic energy conversion, we have to really digest the relationship between science, knowledge development, technology and technological development, of course, industry and business development. Unless you complete this, I should say, this triangle, this is a triangle of science, technology, and industry. Sometimes it's called holy triangle. Unless you complete this, progress is slow. So where are we with photovoltaic completing this holy triangle? Let's have a look at some figures in photovoltaic very, very quickly. Over the years, everybody is trying to really utilize the energy in the sun. But in the visible region, as you can see, has the 50% of the solar energy, and you've got 44% in the infrared and infrared region, and 6% in the ultraviolet region. But there are sort of generations of solar cells start from 1G to 4G. As you can really imagine, 1G generation is really on single or polycrystalline silicon as well as gallium arsenide cells. Currently, 95% of the market belong to them. Second generation thin film, third generation dye-synthesized solar cells, organic polymeritic solar cell, perovskite solar cell, quantum dots, etc. And the fourth generation, that's what we are really concentrating on, the low-cost, flexible polymer thin film transparent photovoltaic cells employing nanomaterials. This is metallic nanoparticles, metal oxide, fluorines and derivatives, graphene and derivatives, etc. This is the kind of new area photovoltaic community is concentrating, and there is a significant excitement really in the community to work on this. Currently, we know this all the value of efficiencies in solar cell scales and solar module scales. They are really going up and up and up new applications. But over the year, when you look at that, the multicrystalline silicon cell, monocrystalline silicon cell really competing with each other. And in the 1990s, the thin film started gaining some momentum, but recently it's very small. But one has to watch this area. I am warning the young scientists. Thin film photovoltaic materials has significant potential when it is applied together with nanotechnology. Okay, nanotechnology in photovoltaic energy conversion. Okay, designing nanoscale surface structures to improve tunable absorption and reduce reflection. Transparent low resistivity contact for charge collections. Nano coatings for improved efficiency. designing innovative solar cell structures, enhanced light coupling, engineering interfaces, bandgap engineering. You can see new horizons to work with theoretically and experimentally. There are plenty of room at the bottom, as Feynman said. Okay, you said, currently 95% of photovoltaic market is by crystalline silicon cells. Of course, nanotechnology is applied at each value chain, but I will be really giving two examples to really give this some appetizer. One is really how you're going to really improve efficiency further. As you can see, the tandem cells are really gaining the big interest in the field. We will be see tandems, and still nanotechnology is not in the scene yet in this. And the module goes the same way. But when you think of silicon, silicon has a high refractive index material. Refracting index is 3.52 at 120 nanometer at 2093 Kelvin. That's why we've got high reflection losses. Since it's an indirect bandgap semiconductor, we've got problem with the absorption, low level absorption. So how we can really improve those using nanotechnology? Probably some of you heard black silicon and silicon nanowires. When you say black silicon and silicon nanowires, we are talking about really processing the surface. Surface, as you can see in surface, like nanowires on the crystalline silicon surface, which doesn't allow you to reflect, absorbs everything. It could be in black silicon micro scale or nanoscale, and both micro and nanoscale, including various structure, holes, needles, etc., is now applied in really making better silicon solar cell. And you've got horizontally grown silicon nanowires on silicon surfaces to improve, again, absorption in a silicon. When it comes really changing the surface feature, the second thing you can do is putting some metal nanoparticles on silicon solar cells. If you have, for instance, it's a schematic showing of, if you've got silicon surfaces with needles or pyramids or the cones, there have been some interesting simulation using all these. What could be the gain? You can have the absorption spectra simulation using fine and difference time domain simulation process. As you can see, lambda is the wavelength of the incident light, transmittance spectra, and reflective spectra. Metal nanoparticles, what they do? They promote incident light to scatter at different angles, which gives a hell of a lot different higher absorption. Light path length through the solar cell spread increased significantly. And you can really read all of those, and you've got a gain of, as you can see, for putting metal nanoparticles, in this case, it's a gold in this simulation, on the surface. You can see the change is not that significant. This black curve is representing Lambert limit, which is 4n squared. But when you have the cones, you can see the significant change in absorptions, and cones also give you significant improvements. So using nanotechnology, you can use significantly higher absorption surfaces in silicon. What it gives, of course, what's happening is there's a kind of interesting area in physics called plasmonic physics. There's a plasmonic effects in the nanoparticles, metal nanoparticles. So you create a surface plasmons. Surface plasmons propagate the interface to the metal and surrounding the electric medium. The resulting electromagnetic wave is strongly confined around the metal nanoparticles, adding to incident field, giving to the near field enhancement through the localized surface plasmons resonance. This has significant effect. In fact, recent work by Zaman S. and Hussein M. gives some electric field changing for different geometries coated with gold nanoparticles. As you can see how much increase you can have in the electric field. The third ones in here are the really enlarged version of the second column. There's an interesting changes and there's an important observation to be able to apply for improving solar cell efficiencies. This figure, how you calculate solar cell efficiencies when you've got increased absorption using the discussion we've been going through. And it is suggested that if you use a nanopyramid is the best one, we can have up to 40% efficient solar cells using nanotechnology and existing silicon technologies. This is one example of silicon. If we sort of really talk about time is limited, on the organic, we should talk about how we can really, because when you say think of silicon, silicon is confined in the visible region, and because of one gap is 1.1. If you are really interested in really achieving higher efficiencies from different parts of the solar spectrum, you should look into the actual photon flux. In fact, when you calculate the photon flux, you can see 73% of the photon flux is in the near-infrared regime. So if we find a way of utilizing these photons, converting into electricity, electron pairs somehow, you have another opening for the photovoltaic system. How we can do that? We can do that with nanotechnology. But when you really do that, you have to think of if you have a system allowing the visible region, what will be the region you should allow, and what are the region you should be utilizing to convert into electricity? In here, when you think of the visible region, it changes depending on the reference, but between 390 and 700 nanometer. But we don't really see all of it. What we are interested in the photopic vision, where we have the vision in the light conditions bigger than 3 candelas. There are mesopic vision under 3, and there are scotopic vision for very, very low light level. If we really allow this region going through, we can really don't bother very much about those. Of course, the other thing is the haze color assessment. And when you have the coating, you have to be really transparent photovoltaic, which is acceptable by the end user in sense of haze, color rendering, etc. That's why really we are currently with conventional cells, we are here, but we can really have rather those regions as well to be utilized for conversion. Why we do that? Because this is a big dream. When you think of all the buildings, I show you the 14 highest building, each one is larger than 300 meters. They have all glass. Surfaces are all glass. If we can really put some layer which convert sunlight into electricity, but it can be accepted by us for a visual, it will be a big gain. Let's just say, imagine this, how much potential there. So we should really work that, and people are working on it. So when we look at the transparent photovoltaic cells, aesthetic is important, efficiency is important, cost, production, thickness. Again, nanotechnology coming to scene in here, very fast. Time is getting, this is how you calculate the efficiency. There are 3 approaches. Wavelength selective transparent organic photovoltaic cell, luminescent solar cell concentrator system, novel designs. Probably you heard the luminescent solar cells, which is really used in nanotechnology, absorbed, emit the light to the side of the windows and convert to the electricity. Time is, again, you can see how much the nanotechnology and playing with the molecules and making tailoring of molecules important in this sense. I've got 5 minutes, so I have to go fast. And dual band result in here, as you can see, significantly higher results already obtained. The other one is optical value, how you calculate in there. The organic photovoltaic cells, small molecules, polymer-based, and dye-sensitized solar cells. Probably you heard some of that. I'm not going to go in detail about HOMO, LUMO levels, very much really related to our valence band, conduction band, energy bands in the conventional inorganic photovoltaics. The same applies there. What happens is simply you create excitons, which has been discussed again before. And you create excitons and you sort of collect somehow. But when you do that, how you can do that efficiently again, it comes in the nanotechnology. Active layer in the solar cells is about 100 nanometer, and the two components are separated only by 10 nanometer scale. Initially, it started bilayer OPVs, now is a bulk heterojunction or photovoltaics is in the scene. Very quickly, in 2015, we had 11% efficient organic solar cells. Now it's 18% efficient solar cells, and they are stable. And again, as you can see, single junction non-fluorine organic cells are getting better because fluorine has some problems. So the nanotechnologically, we are playing with molecules one by one, changing and creating new approaches. These are the very good areas to work with. Recent results show that non-fluorines are getting better in 2020 compared to fluorine in efficiencies. But stability, non-fluorines has some problems compared to fluorines. Okay. There are improved properties by several groups, and mainly United States is working on transparent organic photovoltaic cells. These are the very recent design. They employed everything possible, reflection of the light using nanotechnology and having multiple molecule structures to create, let the photopic region go through and absorbs the other parts of the solar spectrum to convert sunshine into electricity. This is their results. There are big companies really working on it, mainly Solaria, some partners, and Heliatech, Onyx Solar, Follow Solar, etc. There are companies seriously producing those on a pilot line. This is some results of ubiquitous energy and 5Z energy. They are really soon on the market. The big glass company called NSG, Japanese company, really bought ubiquitous to produce transparent photovoltaic coated glass for buildings. Well, for the appetizers, getting close to lunchtime, give me a couple of more minutes. Who are doing what in this area? Probably you might contact to really get more information and possible collaboration. For instance, in MIT, a method manufactured larger defect-free sheet of graphene for use light-weight solar cells, phosphorine nanosheet to build a temperature perovskite solar cells. This is a university in Australia. Honeycomb light structured graphene, which graphene sheets. This is Michigan Technological University. They use the 3D graphene. Copper indium selenide sulfide quantum dots. Los Alamos is working on it. Solar cells made for a single molecule thick sheets, MIT again. This type of solar cell could produce 1,000 times as much as power for a given normal photovoltaic devices. Graphene coated zinc oxide, MIT. Semiconductor nanowires, MIT. A gold nanomesh, 30 nanometer thick to eliminate losses due to reflection, Princeton. Nanocubes, Duke University. Nanowires, Niels Bohr University. Thermophotovoltaic. This is an interesting area for everyone work. they use a carbon nanotubes to convert light to a heat, and photonic crystal to convert that heat to light and absorb in the photovoltaic devices. And it goes like that. So nanotubes, nanowires, they're all over the world. People are very much interested in, either physicists, chemists, and material scientists working on it. Okay, pros. There is a potential. Designing nanoscale surface structure, transparent low-resistive contacts, nano coatings, ability to design innovative solar cell structures, enhanced light coupling, light engineering, interface engineering, bandgap engineering, novel organic transport, etc. And of course, there are cons. The actual cells not really big enough for commercialized, apart from a couple of new area, but soon we'll be seeing these applications in the larger scales and commercially available on the market. So applications of nanotechnology to photovoltaic conversion is one of the horizon for the photovoltaic industries, scientists, and researchers. Thank you very much for listening to me. If any question, I can try to answer.
Thank you very much for your nice talk. And you would like to get questions. Is there any question? There's one question here.
Thanks for your nice presentation. I have a question about how it can be more better. Is there any other materials for that, or do you have any advice to work on it?
First of all, could you tell me what are the area are you working on?
I'm just high school student and I'm just curious.
Okay. Well, if you are a high school student, fundamental science are the key for everything. If you are interested in experimental or theoretical, you can go to a material science working on physics or chemistry, or mathematics is of course a very nice area, but it is kind of a different appetite you need for that. If you are really hands-on guy, go to experimental physics. If you like to use the maths to understand what's happening in the world, go to theoretical physics.
Thanks a lot.
Thank you very much. And another question? If not, thank you again, Professor Şener Oktik, for your nice talk. And we are moving on our next speaker, Professor Nihan Kozkuperköz.
Professor Çapan, before I close, can I say something?
Yes, please.
High school student or the university student, if they are interested in anything I've been telling, please contact me. We can discuss further to start something with them. Thank you.
Thank you very much again. And our speakers is from Eskişehir Technical University, and she's going to talk on growth of two-dimensional materials and their device application. Professor Nihan Kozkuperköz, she's going to give a talk. Just 2 minutes. And I would like to say something. We have 1 minute. After this talk, and there will be lunch break. After then, poster section will be start at 2 o'clock in here. We have 2 poster sections. One is on-site and online. Both of them are in this Herodot Cultural Center. Please.
Thank you very much for your kind introduction. It's a pleasure for me to be here, especially in this pandemic period. Maybe this one, yes. It wasn't easy to be on-site meetings, so I'm glad that I'm giving this talk. As you see, the title of my talk is Growth of Two-Dimensional Materials and Their Device Applications. And as you see, I'm coming from Eskişehir Technical University, which is a new university. Formerly, we were Anadolu University. Then about 3 years ago, we separated into two. So it gives us a different kind of motivation with this university, new establishment. Maybe from here. Maybe the battery went off. Not from here. Now it's working. Great. Okay, thank you. Okay, let me return back to the beginning. So before I start talking about our results, I also like to give some basic information on two-dimensional materials, and it's quite linked to the previous talk, Professor Oktik's presentation, because two-dimensional materials are also nanotechnological, scientific, and technological results, outcomes, let's say. So I like this picture to explain, first of all, what are two-dimensional materials? You lose the dimension when you go deep into nanometer scale. For example, if someone says zero-dimensional material, it means that it's a kind of a ball, and none of the dimensions are higher than, for example, 50 nanometers, less than 10 nanometers usually. So two dimensions means it's a kind of sheet of paper, and onion-like materials, you can still peel them off, but you cannot easily get the layers. For example, for onion, if you take one layer, then it means that the bonds in between the layers are weak. Probably you have heard about van der Waals bonds, so that you can get those two-dimensional materials easily. So graphene is the most famous, well-known two-dimensional materials. In 2004, Gaim and Novoselov peeled it off from a very well-known carbon allotrope, and they got few layers of graphene. And 1 year later, they could manage to make it only one layer, monolayer, we say. So this was very interesting. It took a lot of interest because I think I cannot get further away from the microphone because the other is not working. Because for about 60 years, people thought that it's not possible to have stable two-dimensional structures. Thermodynamically, it wasn't possible. So this simple Scotch tape experiment, mechanical exfoliation, showed that it's possible to have a two-dimensional material and it's just stable. And why is it so interesting? Because the properties, the chemical, mechanical, electrical properties were profoundly different from graphite. Graphite is an insulator, however, graphene is the best conductor ever. So people started to work on different two-dimensional materials, also experimentally starting from 2005, and these guys took the Nobel Prize in 2010. So here you see a list of different well-studied, let's say, two-dimensional materials. For example, hexagonal boron nitride is an insulator, different from graphene. Transition metal dechalcogenides, which we also study on, they have very good optical properties, strong light-matter interactions. And apart from that, silicene, phosphorine, borophene, you can see many different types. And researchers think that still maybe more than 500 different two-dimensional materials can still be found. So here you can see again what makes something layered. So what makes something potentially two-dimensional is the weak bonds in between these layers. And the layers are linked to each other usually with strong covalent bonds. Of course, depends because there is a large variety. So just shortly, I like to talk about market share. As Professor Şener Oktik has said, that triangle should be completed for the research to continue. When I was doing my PhD, one-dimensional materials, carbon nanotubes, took a lot of interest, but then the saturation and even loss in the interest occurred because it wasn't easy to produce those carbon nanotubes in a controlled manner. And now it's the question for two-dimensional materials, can they penetrate into the market? And can the investors and people make money out of it by manufacturing, producing devices? So people make estimations and say that the market will reach about $400 million. This will probably not happen, but still the expectation is high and the pressure is also high. And they think that these years are the inflection years. Things can change. So we'll see in a few years' time when indeed these two-dimensional materials will really be used. So what's the problem? Although there is so much investment, big projects, for example, Flagship, Graphene Flagship has been the biggest ever founded project in Europe. That was graphene. So it means that there was a lot of expectation, but it didn't, partially it didn't meet the goals. So what's the problem? The problem is mainly related to synthesis methods. So you need, for the mass production, of course, reproducible and scalable techniques for commercialization. So now let me return back to our two-dimensional materials. In our laboratory, we call Micronano Devices and Systems Laboratory. We have different subjects, but one of the main subjects is to grow, design, and fabricate related materials and devices. So graphene, we grow, like people who deal with two-dimensional materials, that's the first thing to do probably. And transition metal dechalcogenides, they are semiconductors mostly. We also have started to grow MAXenes, a new family of two-dimensional materials. These are metallic materials. And we transfer these on top of each other, or we can grow them in one step in CVD. So make heterostructures or hybrids to get different properties, different functionalities. So let me remind why graphene took Nobel Prize, took so much interest. It is only one layer these you see the carbon atoms, honeycomb shape, and very strong covalent bonds. And it's flexible, but in spite of its thickness, it's very strong. The Young modulus is huge. The tensile strength is very high. And at the same time, it's a very good thermal conductor and electrical conductor. So as I already said, the best ever. And it has a, of course, because it's so thin, the optical transparency is also very high, but it can still absorb some of the light. So some people use it in solar cells as some layers. So although so much investment has occurred on graphene, again, in addition to production technologies, there are some other problems, main physical problems. It's because of this energy band diagram. As you see, there are cones here. People call it Fermi-Dirac cones. So when the physicists look at it, they will immediately see that there is no band gap. And if there is no band gap in a semiconductor, then you cannot easily make a device out of it. Transistors, first of all, MOSFETs or photodetectors, whatever, you cannot control the current. So the current flows ballistically, nearly the electrons fly in the graphene, but the problem is you cannot control it. So what people have done to control this current, they changed the structures, they made thin ribbons, they created topological defects, they had grain boundaries, strains, they applied stress to open this band. But whatever has been done, even if you create a band gap, then you lose the conductivity, that nice conductivity. So to make an active device out of graphene, it's not easy. It's such a nice material to use together with others, indeed. So people are doing those heterostructures, hybrids with graphene recently. How about transition metal dechalcogenized? What does it mean? In the periodic table, transition metals and chalcogenized, if they make compounds like molybdenum, tungsten, we are more interested from the transition metal side, and sulfur and selenium dechalcogenize. When they make these compounds, people call it transition metal dechalcogenized. And when they are in bulk form, their band gap is indirect. Indirect means the minima of the conduction band and the maximum, minima of the conduction band and the maximum of the valence band are at different propagation constants, different K values. So it means that light and matter interaction is low. But when you can make this material in monolayer form, if you can manage it, then this band gap changes with quantum confinement effects, the density of states change. So it becomes a direct band gap material, which means that it can be a better solar cell, it can become a light emitting diode or a laser, so you can play with the light. So that's why, and not only that, these materials are mechanically strong, stable, they are not toxic. So somehow people are always thinking about how to replace, in fact, silicon technology. Maybe you have heard about Moore's law, that the transistors are doubling every 2 years. And all the time, the channel length is becoming shorter and shorter. So now atomic transistors are being fabricated, but it's not still a solution if you think about large systems. So which material system can address this challenge? How can we overcome this problem? So that's why people have thought, why not TMDCs? And they have very high on-off ratios and other nice properties. So when you grow it, there are three possibilities. It has three phases. One is 1T, which is metallic. 2H and 3R polytypes are semiconductors, but mostly this 2H phase is mostly studied. And here you see how the band gap changes from bulk to the monolayer form. In the bulk case, for example, the most studied one is molybdenum disulfide. It has a band gap of 1.2 electron volts. And when you get one layer out of it, it becomes 1.8 in the visible range. So it can shine in red. And the same thing is true. The same shift we can observe for tungsten disulfide, molybdenum diselenide. This is in the infrared 1 point. It's getting close to the infrared 1.5 electron volts. Here you can see the band gap change maybe more easily. The first one is hexagonal boron nitride. So it has such a large band gap. It can be used as an insulator. For example, remember the most used transistor type is MOSFET, metal oxide semiconductor field effect transistor. So you need a metal, you need an oxide, and you need a semiconductor, two-dimensional layer, let's say. We are just imagining. So somehow in this range, you can get these. This can be an insulator layer. And graphene can behave like a metal. As I said, people call it semi-metallic because in metals, the Fermi levels, the conduction and valence bands overlap with each other. But graphene is just in between, not a semiconductor, not a metal, but it can be used as a metal. So the others can be the active parts to control that conductivity, the current. And among these different two-dimensional materials, I find phosphorine also quite interesting because when you change the number of levels, that band gap changes from 0.3 electron volts in its bulk form. When you decrease the layers, it can become in monolayer 2 electron volts. But it has again problems. It's not very stable under ambient conditions. So each two-dimensional material, although they have a high potential, there are still practical problems, I can say. So up to now, after graphene, these TMDs have also taken a lot of interest and they have been implemented in different devices, as you see here. Two-dimensional materials are nice to be used in the gas sensors because think about it, two-dimension means all the volume is the area. So the area and the volume are the same. So if a gas particle absorbs on this area, it means that the IV curve, the characteristics of this active part will change. So the sensitivity will be much higher than its three-dimensional form. So that's why people are already, in fact, manufacturing such kind of two-dimensional sensors. And as you see, it is very, again, high potential in optical applications also. So another one, MXenes. This is different from the other two-dimensional materials because in usual case, the layered ones have the van der Waals bonds in between. But this one is more strongly bonded. So you cannot mechanically exfoliate, for example, MXene out of MAX. By the way, I'm sure you have realized people use this "ene" suffix to mean something two-dimensional, silicene, borophene. As you see, this one is MXene. So this was a mineral long time ago discovered. Then in 2011, Gogotsi and his friends, I think in Cornell University, they discovered that from the MAX phase, they can produce two-dimensional materials also. How do they do it? They chemically etch these A atoms out of it. What are the A atoms? As you see, these could be, so there's a large, very large variety of possibility of Mach spaces and Maxine structures also. So you need to get rid of these A group elements to get Maxine. And you remain with this one, this layer. And what is that? As you see, early transition metals, and X represents carbon or nitrogen. So this is the metallic two-dimensional material. It can also be a superconductor, and even they have established a company, and they are producing and selling to the world such kind of Maxine structures. However, we are not sure if this chemical etching is the best method to get Maxines, because when you use solutions to produce something, especially toxic solutions, hydrofluoric acid is used here, it's not very environmentally friendly, and also some functional groups such as fluorine, hydrogen, or hydroxyl groups remain there, remain in the Maxine structure. So theoretically, people predict very nice values of conductivities, either thermal conductivity or electrical conductivity. But when they produce in this way, the performance parameters degrade. So it means the device parameters also degrade. So there should be some other ways to produce, again, Maxines. And here, this is a previous research of us, only theoretical, which Maxine compounds are stable and which are not stable. So which ones should we produce in our laboratory? We should try. Here's a timeline of Maxine research, and the blue ones all show different people producing different Maxines by using chemical etching. And we say that, although it's very difficult to see because of the resolution, I think, that green one is produced by chemical vapor deposition. So that's the way we use also in our laboratory that I'll be talking about. And these are the properties of Maxines. Mostly defense industry is interested in Maxines because they can be used in avionic components, as they have that high electrical conductivity and thermal conductivity, and they are very strong materials again, so they can be integrated into composites to increase the performance criterion again. Other from that, also energy storage applications, Maxine seems to be quite appealing. People use as electrodes in lithium-ion batteries, sodium-ion batteries, and in our group, we make supercapacitors out of Maxines, and also using graphene. So it's possible to use it at different devices as the metallic parts, metallic components. And another important field that can be applied is, again, optoelectronics, because it's difficult to make these two-dimensional devices, as you need to communicate with the outside world. For example, if you make metallic contacts, then you can have Schottky barriers, which usually happens in our transistor fabrication also. So to get rid of that problem, some other types of structures are being worked on, and Maxines, when you hybridize, when you make a Maxine contact on top of, for example, our TMDCs, then this Schottky contact problem is overcome, and we have an ohmic contact. So at the end, I'll show a kind of schematics showing that everything could be out of two-dimensional materials. So we're thinking if Maxines could be the metallic one for those devices. as I'm from the electrical and electronics engineering, I always try, I think about the device application part at the same time. Although we have spent a lot of effort on physics and materials part also. So now let me talk about our own results and how we try to obtain these two-dimensional materials. Çok yavaş gittim. Okay, thank you. So in general, exfoliation has been used most commonly. As I said, Gaim and Novoselo also obtained that first graphene by using this technique. But it's problematic because the flake sizes are very small and you cannot use it in a factory to have mass production. So what are the other possibilities? People use molecular beam epitaxy, which is a very expensive technique again, but it's possible, of course, and chemical vapor deposition, atomic layer deposition techniques, so which we have in our laboratory. And these are simple and cheaper, but the problem is the ability of controlling these. It's a simple, what is chemical vapor deposition? Anything which heats, there's a chamber, you have vacuum, you heat some precursors, you flow some gas, and you make some compounds with some chemical reactions. So that is chemical vapor deposition, and it can be in different shapes. So, but in our case, to manage to have two-dimensional materials, it has to be a little bit special. Because think about it, only one layer, you want to control, you want to grow only one layer and not more. So that's why we use a mobile heater body. So whenever the process is finished, we move this heater to stop the process. And also split furnace, again, to get rid of the heat out of the small chamber. So that's why we use such kind of a homemade, let's say, because we combined different parts of it, chamber. And how do we characterize our two-dimensional materials? This triangle is a molybdenum disulfide monolayer flake. So we use optical microscopy, Raman scattering spectra, Raman spectroscopy, photoluminescence. Why? Because when this structure TMDC is one layer, it absorbs light and it emits light. But when it is two layers or three layers, this emission drops. So photoluminescence easily tells you if you have really monolayers or not. And of course, the most important thing is still to prove that you have one layer. AFM is a good way of showing it. So about 0.7 nanometers of thickness we have. For graphene, that's 0.3 nanometers. So indeed, very thin materials you need to grow. So as I have very little time, we played with this setup quite a lot. We put precursors into different places. We used the substrate as face down, side by side. Why? Because we obtain these triangles, but at some locations that we don't know. The control is not very high. So we saw that the distance from the precursors is very critical to get those monolayers. I think I need to be quick. Sometimes we got nanovolts, sometimes particles, but only at some narrow regions we got the triangles. And the distance in between these two EG and AG peaks tell us also if we have a monolayer or not. These two peaks start to get closer when you have the monolayer. It's about 20 per centimeter, but it becomes 25 when it is in the bulk form. So AFM, atomic force microscopy, is a nice method, is a direct method, but it's difficult to measure each flake. So Raman is a fast way of determining if we have a monolayer or not. and photoluminescence. So I think I'll get, so you can see very different shapes. And the problem is we don't have uniform formation. So this is from a paper from 2016, as far as I remember, where we were trying to understand the growth mechanism. And we changed a lot of parameters. We used hydrogen together with nitrogen as the flow gases. We changed the ratios of the sulfur to molybdenum trioxide precursor, and so that it directly affects how these monolayers form. So again, you see these triangles, large triangles, and sometimes circular shapes. So we wanted to find a better way of producing. Çok az kaldı hocam. Very little time. I'll wrap up. Sorry. Okay. So I think I should show you our device examples. So these are the Maxine growth examples. What we have done, we have fabricated transistors out of these. Here you see as the active layer, only single layer of the active part. This is a MOSFET, backgate MOSFET, and we compared their performance criterion for molybdenum disulfide and tungsten disulfide. And we integrated, hybridized our two-dimensional materials with nanoplatelets to increase the absorption coefficient. And later on, we fabricated a photodetector. Here you can see the molybdenum disulfide layer and nanoplatelets, where the photodetectivity is significantly enhanced, 11-fold, with a gate voltage of 2 volts. So, and this is the supercapacitor example, how the capacitance and is boosted by using suspended layers of graphene as the electrodes. So I didn't put some conclusions part, but I just want to conclude, as Professor Oktik said, there's a lot of room at the bottom, and maybe we say that two-dimensional materials could be a solution to use that atomic level space at the bottom. And we can make such kind of devices by using different two-dimensional materials. Thank you very much.
Thank you very much. This nice talk. And unfortunately, we are not taking any question because there will be another meeting in here. Professor Nihan in here. If you have a question, please, we can have a break, and after that you can ask any question to her. Thank you very much again, and I'm closing this section. Thanks a lot.